A visitor crosses the inner dark, its halo swelling, its light uncertain. For a moment, the biggest eyes in space seem to follow every breath. Then, as the encounter nears, the updates thin. We are told geometry is unkind. We are told patience is wisdom. Yet coincidence breeds questions. Why would the most photogenic phase arrive just as public vision narrows? Stay with this story, because beneath the quiet there may be a simpler, stranger answer than anyone expects. Consider how our relationship with the sky has changed. For decades we learned to expect a river of images. Planet flybys arrived with immaculate portraits. Star nurseries appeared in color that felt like stained glass. When a rare interstellar traveler enters the scene, our first instinct is to wait for the next reveal. Early on, a few frames appear, and they are enough to trigger wonder. The object glows with a rough envelope, a breath of dust and gas that hints at a heart we cannot yet resolve. Then, the cadence fades. The feeds go still. It feels like the curtain has fallen just as the play begins. There is a practical answer, and it starts with the Sunday. Most space telescopes and many ground observatories live by strict safety rules. They keep a respectful distance from direct solar glare. Point too near and detectors risk damage, or scattered light turns data into noise. As the visitor moves across the sky, the angle between it and the sun shrinks. Engineers call this solar elongation. At small elongations, pointing becomes a gamble. Astronomers can also be blocked by the simple fact of daylight and horizon, since even the largest mirror cannot outstare noon. These constraints carve natural holes in the timeline of public images. There is also the quiet rhythm of science, which favors understanding over spectacle. Spectra can tell more than portraits, yet spectra demand patience. A spectrum is a barcode for chemistry and temperature. It takes careful calibration, correction of instrumental quirks, subtraction of background glow, and cross-checks against known lines. If the fingerprint looks familiar, the path to publication is short. If it looks odd, teams will slow down, not to hide, but to avoid telling a story that they might later retract. Analysis is not a cliffhanger, it is a process. Silence then becomes a Rorschach. People project meaning onto it. Some see caution, others see control. But before we judge, we should ask a smaller question. What counts as silence? An instrument may continue to watch, yet publish nothing because the geometry is poor or the signal is weak. Another team may post a quick note in an archive that never reaches headlines. A third may choose spectroscopy over a pretty frame, so the public does not have an image to pass around, though the science continues. What we call silence may simply be misaligned expectations. We want a postcard. The data arrive as spreadsheets. Still, the timing invites curiosity. The visitor approaches a close pass with a nearby planet. Heating increases as distance to the sun falls. This is exactly when comets often transform. Jets can flare. Colors can shift with changing molecules in the coma. Dust trails can thicken and twist with subtle forces. If the story is getting interesting, why do the pictures slow? The unromantic answer is that orbits do not care about our desire for drama. They care about angles and light. The period of maximum change can sit inside the period of worst viewing, especially from Earth. There is also the queue. Big telescopes schedule months in advance. They can interrupt for targets of opportunity, yet that is rare and must meet a high bar. Observers share time across many fields. Distant galaxies, exoplanet atmospheres, dying stars that flare without warning. A newcomer from interstellar space is compelling, but so are the promises already made to other investigations. The queue is not a villain. It is the only way to keep a fleet of instruments healthy and fair, if all. Spite of this sounds like a plea for patience. It is also a map for what comes next. The lull will not last. The visitor will move away from the sun in our sky. Elongation will widen. Data pipelines will catch up. We will begin to see a second wave of results that cover the period when the object was closest to heat and to planetary vantage points. Some of those results may not look like glossy posters. They may be plots of brightness against distance. They may be line lists that mark carbon dioxide, cyanogen, or dicarbon. The pictures will follow, because even analysts like to show, not only tell. Here is the promise of this investigation. We will keep two thoughts in view at once. Known constraints that make silence ordinary. open questions that make this visitor interesting. The known tells us why gaps appear. The unknown urges us to keep watching anyway. Between them lies the real drama, which is not a hidden scandal, but the slow conversion of hints into knowledge. That is the pulse of astronomy. That is the way wonder matures into understanding. So we begin with quiet, not as an accusation, but as a puzzle. If the cameras fell silent for reasons we can explain, then the next step is to rebuild the calendar of what was seen and when, so that evidence replaces rumor. The trail is there. We only need to walk it with care. In the next part, we will reconstruct the timeline, instrument by instrument, and let the pattern speak for itself. Begin with a simple question. What do we actually know about the observing sequence? Early activity featured quick public notes that confirmed the visitor and showed a modest envelope. Then, the cadence slowed as the object slid nearer to the sun from Earth's point of view. To make sense of that change, we rebuild a clean calendar. Not a rumor feed, but a chain of instruments, modes, and viewing angles that explains why some things were seen promptly while others slipped into analysis. The first chapter belongs to survey work. Wide, field searches are designed to notice motion against the starry background. They deliver time-stamped detections that fix a path through space. These survey frames are not glamorous. They are proof of life. Once a path is computed, larger facilities can plan deeper looks. A handful of early images arrived from major observatories. They showed a condensed glow, a coma that suggested volatile ices beginning to wake under sunlight. At that point, the story was simple and bright. A stranger had entered the neighborhood. Cameras turned and curiosity rose. Soon, the geometry tightened. Solar elongation began to shrink. Telescopes that thrive on faint contrast prefer large angles from the sun because scattered light falls away and hardware is safe. As the angle narrows, even space telescopes face stricter rules. Pointing near the sun can introduce stray light that washes a weak target. In some cases, protective limits ban such attempts. Ground observatories suffer a second constraint. The visitor may be above the horizon near twilight, when air glow and atmosphere conspire to dull sensitivity. The timeline bends under these pressures, and release schedules reflect that bend. Meanwhile, not all data are created equal. Imaging satisfies the eye, but spectroscopy satisfies the mind. Teams often pivot to spectra when pictures become hard to obtain or hard to interpret. A spectrum can be taken in shorter exposures, then stacked and calibrated to reveal faint chemical fingerprints. Water, carbon dioxide, cyanogen, and dicarbon each leave distinct marks. If those marks agree with expectations, results can move quickly through internal checks. If the pattern deviates, teams slow down. That slowdown populates our calendar with quiet intervals that are not empty. They are full of work that is invisible from the outside. Another thread in the timeline is queue management. Major facilities book their nights and orbits long in advance. There are pathways for urgent targets, yet those pathways have thresholds. A rare interstellar object is compelling, but so are previously approved programs that answer long-standing questions about galaxies, star formation, or planetary weather. When the visitor enters the high-interest phase, just as solar geometry worsens, the incentive to interrupt other programs drops. The likely yield from emergency imaging is low. The chance of damage or poor data is non-trivial. The queue holds. The calendar reflects that choice. There is also the reality of pipelines. Raw files must pass through calibration steps before they are fit for analysis or public use. Bias and dark frames remove instrument signatures. Flat fields correct pixel variations. Stars become fixed points for alignment and stacking. Cosmic rays are identified and rejected. For a bright nebula, this work can move briskly. For a small moving target near the glare of the sun, the work can require custom treatments. Those treatments elongate the path from observation to announcement. Our timeline inherits that elongation. Public platforms distort perception of time as well. A quick post of a stacked amateur image can appear hours after a clear night. An institutional release that follows quality control can appear weeks after the photons were collected. When a late release carries an earlier observation date, it can read like a gap rather than a product of careful processing. The calendar feels sparse, even as the lab notebooks are crowded. Recognizing this lag keeps our reconstruction honest. If we lay these strands together, the pattern is less mysterious. Early survey detections build a track. First portraits arrive, while elongation is friendly. The object moves closer to the sun from our line of sight. Safety rules and glare disfavor fresh portraits. Spectroscopy takes the baton because chemistry can still be measured when shapes blur. Pipelines fill with spectra and hard-to-process frames. The queue holds to its promises. Public channels quiet down. This is not a vanishing act. It is astronomy under constraints. The value of a rebuilt timeline is not only historical, it prepares us for the next phase. As the visitor rounds the sun from our perspective, elongation will widen. Vantage points from spacecraft around other worlds may add views that Earth cannot obtain. Data taken during the difficult weeks will reach the end of their pipelines and emerge as plots, line lists, and eventually processed images. When that happens, we will be able to compare chemistry, structure, and brightness across the very interval that felt silent. We can now hand the story to geometry. The next part explains why the angle to the sun is destiny for any small icy body, and why safety limits are not excuses but guardrails that keep our best instruments alive for the long game. The simplest number in this story is an angle. It is the separation between a target and the sun, as seen from the observer. Astronomers call it solar elongation. When elongation is large, the sky near the object is dark, and the risk to instruments is low. When elongation shrinks, scattered sunlight floods, optics and safety rules begin to rule the night. This single geometry can mute a dramatic sky. Every precision telescope lives inside a protective culture. Baffles, shields, and strict pointing rules keep direct sunlight and reflected heat away from fragile detectors. Even a brief exposure to near-solar glare can overwhelm a camera, knock a sensor out of its carefully controlled temperature, or fill an image with a storm of light that looks like snow. To prevent that outcome, operations teams defined forbidden zones around the sunday. Within these zones, the telescope cannot point. The exact boundary depends on the design of the observatory, but the idea is the same. Protect the instrument first, then pursue the target. Space-based instruments face another enemy besides the sun itself. The bright sky that surrounds the solar disk does not end at the edge. Light scatters through mirrors and structural supports. It bounces inside the instrument in subtle paths. Some light leaks through the outer wings of the point spread function and washes across a field. Even a modest amount of this stray light can destroy the contrast that a faint comet needs. A camera built for deep galaxies can see a face on spiral at the limits of the universe, but it can be powerless against a small dusty halo that sits close to the sun in the sky. Ground observatories add atmosphere to the list of difficulties. Twilight creates an elevated background that reduces sensitivity. Air molecules and aerosols scatter sunlight across the sky, which brightens the background even when the sun is well below the horizon. The thicker air at low altitude near the horizon adds turbulence and extinction, so the path through the air dims and blurs a faint source. A target that would be simple at midnight high overhead becomes marginal when it hugs the evening or morning glow. The visitor in our story spent parts of its arc in exactly that compromised regime. Infrared observations that would normally pierce dust face their own limits. Warm optics glow in the infrared, like a faint ember. Engineers cool instruments to suppress that glow, but extra heat from pointing near the sun can push systems toward unwanted equilibrium. When thermal margins tighten, operations teams grow conservative. Better to wait for a safer angle than to risk a drift in detector temperature that will take days to unwind. The same caution applies to gyroscopes and star trackers. Near the sun, the guidance sensors see fewer reference stars and more scattered light, so pointing becomes less stable. The entire system becomes less forgiving. Coronagraphs and solar observatories can look near the sun because they are built for that job. Their optics include masks and occulters that block direct solar light and its immediate glare. They are not general-purpose cameras for faint comets. Their fields are narrow, and their sensitivity and filters are tuned to the solar wind and the corona. A comet that passes through such a field can be recorded on occasion, but that is an accident of geometry rather than a reliable plan. The instruments best suited to study this visitor are the ones that must obey sun avoidance rules, so our calendar of images inherits those rules. There is also the rotating stage of the solar system to consider. Elongation depends on the positions of Earth, the target, and the Sunday. A comet can be physically far from the Sun and yet sit close to it in our sky. The reverse can also happen. The same object can be well placed for a spacecraft at Mars, while it is poorly placed for Earth. Two observers under the same star can tell different stories because their lines of sight differ. A period that looks like silence from one vantage point may be alive with data from another, which will arrive later through downlink and processing. All of these constraints are not excuses, they are the cost of doing careful work. The public is right to want pictures, scientists want them too. They also want instruments that last for decades, and images that are clean enough to support real conclusions. When a comet moves into a geometry that threatens those goals, the correct choice is to slow down. That choice carves a gap in the visual record. It also forces a pivot toward data types that can survive bright skies, shorter exposures, and narrower windows of stability. The limit of seeing near the Sun then becomes a narrative limit as well. It shapes what can be shown and when. It nudges teams away from portrait work and toward elemental fingerprints. It pushes audiences to accept that some phases of a cosmic story must be told in numbers rather than in posters. This is not a loss of wonder. It is a change of instrument. Chemistry can speak when images fall quiet, and chemistry often tells the deeper tale. Which brings us to the next move. If portraits fade as elongation shrinks, then spectra rise to carry the plot forward. A spectrum can survive glare that would ruin a picture, and it can reveal what kind of ices and gases drive the show. In the next part, we will see how lines on a graph can outtalk a perfect photograph, and why the slow path through analysis is sometimes the only honest path to truth. When the sky grows bright and portraits turn difficult, the story does not end. It changes language. Pictures speak in shape and texture. Spectra speak in lines and ratios. Where an image gives a face, a spectrum gives a fingerprint. For a comet or any icy traveler, that fingerprint can be more revealing than 1,000 clean frames because it tells us what is actually leaving the surface and how fast sunlight is unlocking the chemistry within. A spectrum begins as a simple act. Spread the incoming light into its colors, then measure how much arrives at each narrow slice of wavelength. In those measurements sit troughs and peaks that correspond to specific molecules. Water leaves signatures in the near-infrared. Carbon dioxide writes in bands that are strong and crisp. Carbon-based fragments such as dicarbon and cyanogen carve out narrow features in the visible and ultraviolet. The exact wavelengths are not arbitrary, they are set by quantum structure. Electrons in molecules can jump only between allowed energy levels, so they absorb and emit light at precise colors. When those colors appear, they are not guesses, they are labels. This is why teams pivot to spectroscopy when images stall. A picture near the Sun might be bathed in glare or contaminated by scattered light from the optics. A spectrum can be taken in shorter slices of time, then stacked in ways that recover signal while suppressing the unwanted background. Calibration steps that look tedious on paper are the very tools that turn a noisy observation into a chemical census. Dark frames and flats remove instrument quirks. Reference lamps set the wavelength. Scale. Standard stars fix the relative throughput so that the shape of the continuum is real and not an illusion of the instrument. The payoff is direct. If water dominates, we expect certain bands to swell as the object warms and approaches the Sunday. If carbon dioxide is unexpectedly strong, the spectrum will show it, and it will do so even if a pretty photo cannot. If the coma appears green in photographs, a spectrum can test whether dicarbon or cyanogen are truly responsible, or whether color processing fooled the eye. In this language, a slight shift in a line or a change in strength across days can be more dramatic than a dazzling portrait. It is the difference between looking at smoke and reading what burns. There is a reason, however, that these results do not arrive overnight. Spectra thrive on caution. Small errors in background subtraction can mimic or erase faint features. Imperfect removal of telluric absorption from Earth's atmosphere can plant false lines that masquerade as comet chemistry. Even in space, instrumental response curves can tilt the continuum and hide weak bands under subtle slopes. Teams correct these problems, then they test their corrections by injecting synthetic signals and recovering them, a practice that guards against self-deception. Only when the features survive these trials do they graduate from hints to claims. Spectra also bind the narrative to physics. Cometary gases sublime at different temperatures. Carbon monoxide and carbon dioxide can start to flow farther from the sun than water does. If an interstellar visitor wears a mantle rich in these more volatile ices, its spectrum should reveal that preference early, and the trend should evolve as heat rises. Photochemistry then takes over. Solar radiation breaks molecules and rebuilds fragments, which changes the mix of emission across time. Watching this evolution can separate a simple warm-up from an outburst, driven by pressure and cracking within the nucleus. Light curves can suggest a surge. Spectra can diagnose its cause. When public imagery wanes, it is easy to assume that no one is watching. In truth, the eyes change. Some instruments record spectra rather than images. Others collect slitless data that look like soft frames but are really dispersed light that must be unscrambled into lines. These data end up in archives first as raw numbers, then as reduced products that still require interpretation. Communicating them to a broad audience takes work, because a plot of flux versus wavelength lacks the instant poetry of a luminous tale. Yet that plot can settle arguments that photographs cannot touch. The question of unusual morphology offers a case in point. A sunward-looking feature can spark talk of violated physics or novel forces. Spectra can test the simpler story. They can reveal dust-to-gas ratios and the presence of specific grains that scatter light in ways that emphasize certain directions. They can show whether the coma is dominated by small particles that feel radiation pressure strongly, or by heavier grains that drift differently. Morphology becomes a consequence of composition and size, rather than a source of metaphysical surprise. Spectra also provide a bridge between observers. A professional facility and a skilled amateur with a small spectrograph can both point to the same line and compare strength and shape. That parity builds confidence. It also shortens the time between private insight and shared knowledge. Even when institutions take longer to finalize their reductions, a community of practice can begin to see patterns in the same language and converge on what is real. This is the quiet power of spectral work. It turns a period that looks empty into a period of accumulation. Lines stack into patterns, patterns stack into models. Models predict features that the next set of observations can confirm or refuse. The visitor keeps moving and changing, but the chemistry ties changes to causes instead of to rumor. When the portraits return, they will arrive in a richer context, because we will know what to look for and why. With the language of spectra in mind, we can now face the first anomaly that pushes curiosity higher. Reports suggest an unusually expansive envelope, rich in carbon dioxide, compared with common water-driven behavior. To understand what that means, we need to consider how comi grow and what it implies when the most abundant breath is not the one we expect. That larger question waits just ahead. Imagine a small world that wakes not with the familiar scent of water vapor, but with a colder breath, carbon dioxide pushing outward before anything else. Most comets in our experience behave like kettles on a slow boil. As sunlight seeps in, water ice near the surface warms, turns to gas, and drags dust into a luminous envelope. With this visitor, early clues suggest a different recipe. Carbon dioxide appears to speak loudly, perhaps earlier, and over a wider reach than the water that usually dominates near the inner regions of our system. That shift matters, because the gas that carries the dust sets the stage for how the entire atmosphere looks and evolves. Carbon dioxide can begin to sublime at lower sunlight than water requires. In the colder reaches where many comets first stir, CO2 can already be active, lofting grains before the familiar water-driven phase arrives. If a nucleus is rich in CO2 near its surface, or if fractures open pathways from deeper pockets, the resulting outflow can inflate a coma that feels outsized for the distance from the sunday. The physics is straightforward. Gas molecules leave the surface, collide with one another, and with dust particles, then expand outward into a vast cloud. If the supply is strong, the cloud grows large. If the cloud is large, even coarse dust can be carried farther from the nucleus, changing the way light is scattered and the way tails develop. A CO2 forward coma also hints at how the nucleus might have formed. Comets preserve ingredients from the nursery of their home systems: water, carbon monoxide, carbon dioxide, complex organics, all trapped in a matrix of ice and dust. Ratios vary with temperature history and with the way material was layered during accretion. A traveler from another star could carry a distribution unlike the one common in our own outer regions. That does not imply anything exotic in a sensational sense. It simply means that the chemical pantry can differ across stellar neighborhoods. When we read an unexpected balance between CO2 and water, we are reading a chapter from a different cookbook. Large comets also change the game for interpretation. An expansive CO2 envelope can mimic growth in brightness that appears faster than thermal models predict for water alone. The light we record is a mixture of gas emission and sunlight scattered by dust. If the gas flow carries abundant fine grains into sunlight, the coma can brighten more quickly than a simple water-based curve would suggest. This is why spectra and photometry must travel together. Lines reveal what molecules are present. Light curves show how the total glow evolves with distance and time. The combination tells us whether a surge is real or only apparent. There is a practical consequence for images as well. A big CO2-driven coma can soften structure. Jets that would look sharp in a thinner atmosphere can blur into broader plumes. Features that seem to point in surprising directions may actually be the overlapping projection of many flows seen through a thicker envelope. In that sense, a giant coma both reveals and conceals. It speaks loudly about composition, yet it hides the finer mechanics of the surface unless resolution and contrast are excellent. What could feed such vigor? One possibility is that the nucleus has fresh surfaces that sunlight has not yet hardened. When water dominates over many passages, the upper layers can form a crust of less volatile material that throttles gas flow. A new arrival that begins with CO2 could be excavating new vents before water takes command, so the first act is emphatic. A competing view suggests deeper plumbing. Fractures created by rotation or by thermal stress could open conduits from reservoirs that sit below the surface. Either way, the result is similar. Gas flows, dust rides the wind, and the coma swells beyond expectations set by familiar cases. Color adds another clue. Observers sometimes report a green tint around active comets. That hue often tracks with molecules that shine when broken by sunlight, for example dicarbon or cyanogen. If a CO2-rich coma is also green, spectra can test whether photochemistry within a carbon-heavy cloud is producing abundant fragments that glow in the visible range. It remains uncertain whether color alone can weigh the balance between CO2 and water. Evidence is limited, but one inference is that a carbon-forward environment makes such fragments easier to excite. Until line measurements are public and consistent, color should stay in the realm of suggestive rather than conclusive. If the CO2 envelope is as large as early reports imply, we should also expect interesting interactions with solar radiation pressure. Smaller dust grains feel the push of sunlight strongly. Heavier grains resist it. A powerful CO2 flow can carry a wider spectrum of sizes. That mix affects how tails form and how any sunward-looking features appear in projection. Morphology, chemistry, and dynamics are not separate threads. They are one fabric. The gas you have, the light you receive, and the dust you lift will dictate the shapes you see. The larger lesson is humble. A comet that breathes CO2 first is not breaking rules. It is teaching us that rules come with clauses. Temperature thresholds differ among ices. Layering and fractures matter. The shape of an atmosphere can be written by a gas that is less showy in familiar comets yet dominant here. When portraits return in greater numbers, they will carry hints of that difference in their textures and in the way brightness falls off with distance from the nucleus. From chemistry, we now step to shape. Reports of a sunward-pointing structure have stirred debate about forces and illusions. If CO2 is the lead actor, the dust it lifts and the geometry of our line of sight will decide what looks paradoxical and what is simply perspective. The next part turns that puzzle into a picture you can hold in your head so that shape and gas and sunlight feel like one story rather than three. At first glance, it feels like a rule has been broken. Comet tails should stream away from the sun, yet some images suggest a bright structure that leans toward it. Our eyes read intent into that shape, as if the object were pushing material against the solar wind. Before we leap to exotic forces, we should try a simpler picture that links dust, size, orbital planes, and point of view. With the right geometry, a sunward-looking feature can arise from ordinary physics that plays a familiar trick on perspective. Imagine the comet moving within a shallow sheet of dust that it has released over weeks. Grains leave the nucleus with a range of sizes. Small grains feel sunlight strongly and are swept outward quickly. Large grains respond more sluggishly. They drift on paths that remain closer to the comet's orbit. Over time, these grains populate a thin fan that lies near the comet's orbital plane. If you place your eye nearly along that plane, a dense lane of dust can line up with your sight. The lane can overlap the direction to the sun in projection, so the brightest ridge seems to point sunward, even though the actual push on the dust is away from the sunday. This effect has been described with simple models of dust dynamics for decades. One classic approach separates the history of dust by time of release and by grain size. The lines of equal release time form curves called synchrones. The lines of equal radiation pressure response for a given size form curves called syndenes. Where many synchrones and syndenes overlap in our view, the coma shows enhanced brightness. If that overlap lies along our line of sight toward the sun, a feature appears to lean forward. Nothing in this picture asks the dust to fight radiation pressure. It asks us to accept that a three-dimensional flow looks different when flattened into a two-dimensional image. Grain size matters because it sets how far radiation pressure can displace a particle from the orbit before the comet has moved on. Fine dust can be pushed into a classic antisolar tail quickly. Coarser dust lingers near the orbital track and can create structures like a dust trail or a slab that appears as an anti-tail when viewed near edge-on. The same comet that shows a forward-pointing spike from one vantage point can show a conventional tail from another, or from the same vantage point a few weeks later, once the geometry changes. The sky is a rotating stage. A fixed script can look like a different play from a different seat. Rotation and jets add texture to this canvas. Real nuclei are not smooth spheres. They spin, vent, and precess. Localized sources on the surface can send sheets of dust into preferred directions. If a steady jet feeds the orbital plane with coarse grains, the plane becomes a conveyor belt that builds a bright spine. Even then, the observed direction of the spine is set by our viewpoint. Show the same flow to an observer who sits far from the plane, and the spine vanishes, replaced by a broader fan that points away from the sun as intuition expects. Color and polarization can help test the dust story. If the feature is dominated by reflected sunlight from grains, its spectrum should resemble the solar spectrum modified by the scattering properties of the dust. Polarization measurements can show whether the grains are in the size range that promotes forward scattering, which can make material near the line to the sun appear brighter. If gas emission lines dominate, the feature will behave differently with filters and with viewing angle. One possibility is that a mixture of gas and dust contributes, which would explain changes in appearance as the distance to the sun and the production rates evolve. The role of a large carbon dioxide coma fits neatly into this framework. A vigorous CO2 flow can lift a wider size distribution of grains. More large grains in the plane mean a stronger chance of forming a bright lane that projection can carry across the sunward direction. It remains uncertain whether this is the sole cause in our specific case, but the mechanism is both natural and testable. If the feature persists while the viewing angle changes, or if it fades as the comet leaves the near edge on geometry, that behavior favors the projection explanation. If instead the feature tracks the solar direction regardless of geometry, that would demand a different model. There are limits to what a single image can prove. A true test requires a sequence, ideally from multiple longitudes or from spacecraft with different vantage points. As the line of sight rotates with respect to the orbital plane, the apparent angle and brightness of a projected feature should change in predictable ways. Combined with photometry that separates gas emission from dust reflection, and with spectra that confirm the mix of molecules, the geometry case can be closed one way or the other. This is the advantage of patience. A shape that looks like a paradox in one frame can resolve into a lesson about three-dimensional flows when we watch it evolve. The visitor in our story is not an exception to physics. It is an opportunity to watch familiar physics play out under unusual chemistry and unusual alignment. The wonder remains. It is just anchored in mechanism, rather than mystery for its own sake. If shape can be demystified with viewpoint and dust size, then the next question is whether the reported jumps in brightness are artifacts of method or signs of real changes in activity. Light is a blunt measure, yet it is also the most accessible, and it can mislead if we do not measure it with care. In the next part, we will slow down, and ask how to read a comet's light correctly, so that a surge is not simply a trick of aperture and background. Light curves feel like the heartbeat of a comet. They rise and fall with distance from the sun, with rotation, with vents that open and close as sunlight works into the surface. They are also easy to misread. A chart full of points from many telescopes can look like a sudden surge, even when the apparent jump comes from method rather than from physics. If we want to know whether this visitor truly brightened faster than models expect, we have to slow down and measure light on common ground. Photometry begins with a choice of aperture. Draw a circle around the target on the detector, sum all the counts in that circle, then subtract the sky background measured in a ring just outside. This sounds simple. In practice, it is sensitive to every choice. A small aperture captures the bright core of the coma, but misses diffuse light. A large aperture captures more of the coma, but also more sky noise and more stray light from the field. On a night of high air glow or thin haze, the sky term grows, which makes the net flux look smaller unless the background ring truly samples the same conditions. A consistent aperture and a well-placed sky annulus are the difference between a clean trend and a collection of incomparable points. Filters matter just as much. A broadband green filter will emit different fractions of gas emission and dust reflection than a red filter. An unfiltered camera is a moving target, because its sensitivity curve depends on the detector and on the optics in front of it. If one observer works in a standard photometric band and another uses a clear setup, the two will record different mixtures of light. That difference can mimic a change in activity when the object's color evolves with distance and with chemistry. Standardizing to a common band, or at least reporting the band used, turns a crowd of points into a conversation rather than a debate. Calibration is the third leg of the stool. A 0 point set by comparison stars in the same frame or by standard stars observed in the same night anchors the measurements to known brightness. Thin clouds, variable extinction near the horizon, and color terms between target and comparison stars all tilt the scale. Without proper calibration, a single night stack can claim a big jump that evaporates when placed next to a carefully calibrated series. Evidence is limited, but one inference is that part of the scatter in recent reports comes from mixed practices rather than from genuine surges. Distance corrections are often overlooked. As a comet approaches the sun, reflected sunlight rises approximately with the inverse square of the distance to the sun, while the distance to Earth sets the geometric dilution of light in transit. A fair comparison removes both trends. When we place magnitudes on a reduced scale that divides out these geometry effects, what remains is activity. If the reduced light curve rises faster than thermal expectations for a simple sublimation model, that is a real clue. If it does not, then the seeming surge was a projection effect rather than a new physical regime. Outbursts are the dramatic exceptions. They appear as rapid brightening over hours or days, followed by a slower decline as the coma expands. A competing view suggests that some outbursts are simply phase angle effects near large scattering angles, but a true outburst leaves fingerprints. The coma profile steepens. The color can shift if fine dust dominates the new release. Spectra can show enhanced emission from fragments of carbon-based molecules or from fresh gas. If the visitor experienced such an event, multiple observers in different locations should record a coherent time sequence, not an isolated spike from a single setup. Professional and amateur efforts fit together here. Skilled amateurs can supply dense time coverage that large facilities cannot match. Professionals can offer precision calibration, stable filters, and careful control of systematics. When these worlds meet in the middle, the light curve stops behaving like rumors and begins to behave like a physical signal. One possibility is that early claims of 20-fold brightening reflect a mix of apertures and filters. It remains uncertain whether a sustained excess over models exists. The way to find out is to agree on method and then watch patiently. There is also the matter of where in the coma we measure. A small aperture tied to the same physical size at the comet, for example a radius that corresponds to a few thousand kilometers at the target distance, traces changes near the inner coma, where activity is born. A larger aperture that scales with seeing or with convenience can mix inner and outer regions that evolve on different timescales. Choosing a physical scale and keeping to it yields more comparable results across nights and across observers. If the light curve finally shows a real excess, the interpretation does not need to be sensational. Carbon dioxide can lead to early activity at larger solar distance. Rotational modulation can sweep an active jet toward and away from our view. Fragmentation can create more surface area and a temporary rise in brightness without any mystery beyond mechanical stress. Spectra can discriminate among these options because chemistry and dust size distributions change in different ways for each cause. The practical outcome is clear. When the next images and reports arrive, read the fine print. Ask what filter was used, what aperture radius, what sky annulus, what 0 point, and whether the magnitudes were reduced for distance. If many groups converge on the same rising trend with compatible methods, then a genuine change is in play. If not, caution wins. Either way, a disciplined light curve turns anxiety into a test and rumor into a result. We have treated light as a measure from Earth's vantage. Another vantage sits millions of kilometers away, where orbiters around a nearby planet may catch the visitor during a glancing pass. What can those spacecraft actually see? And how would their results help confirm or deny our inferences from the ground? That is the next turn in the story. When the visitor glides past the orbit of a nearby world, a new balcony opens onto the stage. Spacecraft, that circle that planet, do not share Earth's viewing geometry, and they do not share Earth's atmosphere either. Even so, a distant pass is still distant. 30 million kilometers is a wide ocean of space. The question is not whether a Mars orbiter can deliver postcard portraits of a nucleus. It cannot at that range. The question is, what those platforms can measure that matters. If we ask that question with care, the answer becomes encouraging. Begin with simple optics, resolution scales with distance and aperture. A camera built to map canyons and dust storms on a planet is not optimized to resolve a tiny nucleus far away. At tens of millions of kilometers, the nucleus is effectively a point. What can still be recorded is the shape and brightness of the surrounding coma and tail as a blurred structure, and how that structure changes with time. Even a few pixels across the core of the coma can reveal whether a feature is symmetric or lopsided, whether a fan points in a stable direction, and whether any secondary condensation appears that would hint at fragmentation. Time series imaging from orbit, free of twilight and weather, can supply a rhythm that ground observations might miss during a difficult geometry. Spectroscopy from Mars orbit can play a second role. Instruments that measure gases in a thin atmosphere are sensitive to faint lines and continua. If a spectrometer can be pointed toward the comet against a dark portion of space, it may detect emission from common cometary molecules. Carbon dioxide is of special interest. If the visitor truly carries a dominant CO2 component, even a low-resolution spectrum that confirms a broad band or detects correlated fragments would firm up the chemical picture. The signal will be weak because distance and expansion dilute the glow. Integration time and careful subtraction of the local background will be essential, but the opportunity is real. Phase angle is another advantage. The angle between the Sun, the comet, and the observer changes from place to place. From Mars, the visitor may be seen at a phase that enhances forward scattering by dust grains. Forward scattering can brighten the inner coma and can emphasize structures aligned with the line from the comet to the Sunday. If Earth sees a confusing blur near conjunction, an orbiter with a better phase can extract more contrast from the same physical structure. Comparing brightness patterns at different phase angles also constrains grain sizes, since the shape of the phase function depends on particle properties. This is a case where a single snapshot from a different seat in the theater carries information that multiple Earth-based exposures could not. There are practical limits. Pointing stability and tracking accuracy matter because the comet will drift relative to the background star field. Instruments built for surface imaging usually track the planet, not a moving speck in deep space. Software updates and special sequences are sometimes needed to hold lock on a non-planetary target. Stray light from the Sun must be managed as well. Even in orbit, boresight limits and scattered light within the spacecraft create safe pointing boxes that protect sensors. Teams will balance risk and reward before attempting long integrations on a faint target that was not part of the original mission plan. Calibration and context will decide how persuasive the results are. If a Mars orbiter records a shallow gradient across the coma, those pixels must be anchored to known stars or to instrument standards, so that a change on night 2 is not simply an artifact of exposure or temperature. If a spectrometer claims a line, it must survive checks against instrumental features and against the thin soup of the Martian environment. Cross-calibration with Earth-based photometry and spectra can turn a tentative detection into a robust measurement. The most valuable outcome is not a single dramatic frame. It is a set of observations that can be folded into models of gas production and dust flow that already exist from other vantage points. Even modest success would help answer specific questions raised so far. If the sunward-looking structure is a projection effect from coarse grains in the orbital plane, its apparent angle and contrast should respond to the new line of sight. If the brightness really surged beyond distance-corrected expectations, a stable instrument in Mars orbit can check whether the trend continues on the same timetable. If carbon dioxide is truly abundant, a spectrometer might see associated bands or a linked rise in fragments that photochemistry predicts. Each of these checks does not require detail of the nucleus. They require only consistency and enough signal to trace change. There is also the narrative benefit of multiple witnesses. When two observers separated by tens of millions of kilometers tell compatible stories, confidence grows. A geometry that hid the visitor from Earth may have been favorable from Mars, and data acquired then will emerge after downlink and processing, even if public attention has drifted. The long arc of analysis rewards this patience. A distant pass is not a missed chance. It is a different kind of chance, one that trades sharpness for continuity and trades portrait for pattern. If Mars can add a few firm points to the graph, the next milestone belongs to sunlight itself. As heating increases along the inward path, the physics of sublimation will take over and write new features into the coma. That is where natural stress, outbursts, and color changes often announce themselves. We now turn to that trial by light, and to what it could reveal, even when the ground is still staring through glare. Sunlight is the author of every comet story. As an icy nucleus descends into stronger light, heat seeps inward, and the surface begins to change state. Ice turns to gas, pressure builds in pores and fractures, and vents open where resistance is weakest. In this regime, the coma becomes a living atmosphere that remembers every stress the nucleus has endured. The visitor in our story is entering that regime. What happens next will not be gentle. It will be written by temperature gradients, volatile inventory, and the stubborn mechanics of rock and ice that are held together by ancient glues. Sublimation has a simple logic. Each volatile has a preferred distance where it wakes. Carbon monoxide can begin to flow in deep cold. Carbon dioxide follows at slightly warmer conditions. Water waits for stronger light. As the object approaches the sun, these thresholds are crossed in sequence. If carbon dioxide has already been dominant, then the first leg of the inward journey can be unusually active. As water takes its turn, fresh gas adds to the flow, and the balance of pressure across the surface changes again. Jets that were quiet can ignite. Jets that were strong can choke under rubble liberated by earlier activity. This is why comae evolve. They are not decorations, they are feedback made visible. Outbursts are the fireworks of this phase. Most are local events. Gas trapped under a crust finds a shortcut to space and carries dust with it. The light curve jumps, then relaxes as the new material thins and drifts outward. A careful sequence can distinguish this from a smooth rise caused by distance. Alone, the coma profile steepens near the nucleus. The color can shift toward the blue if fine grains dominate the fresh release. Spectra can show a temporary boost in fragment lines produced when sunlight breaks new molecules. One possibility is that rotation aligns vents with the sun on a schedule, so outbursts repeat with a rhythm. A competing view is that thermal stress opens cracks at random and the pattern will be irregular. Either way, the signs are testable with time series and with filters that separate gas from dust. Fragmentation is the dramatic cousin of outburst. Thermal gradients can pry weak seams apart. Tidal forces near the sun can add stress that was not present far out. When a nucleus divides, the total surface area increases. Gas can escape more easily. Brightness can rise without any change in composition or in heating rate. The coma can develop multiple condensations. A string of pearls geometry can appear if pieces line up along the path. It remains uncertain whether our visitor carries the internal structure that would favor such a break. Evidence is limited, but one inference is that early vigor from carbon dioxide could leave the body more fractured than a water-dominated case. If fragmentation begins, the next images will show it plainly, even if resolution is modest. Color changes are another herald of rising heat. Green hues often grow as photochemistry builds up fragments such as dicarbon and cyanogen in the coma. These molecules glow when sunlight pumps energy into them, then releases that energy as visible light. A greener coma does not automatically confirm a specific chemical ratio. Spectra must do that work. It does tell us that the balance of parent molecules and daughter fragments is changing, which ties back to the inventory of ices and to the rates at which they are exposed. A transition from carbon dioxide, heavy gas, to water-heavy gas can also alter the way dust grains are carried, which in turn changes how light scatters and how tails appear. Phase angle matters here too. Near maximum heating, the comet can present large phase angles to some observers. Forward scattering by dust can exaggerate brightening near the sunday. A careful reduction to remove distance and phase effects is essential before anyone claims activity that exceeds thermal expectations. This is where collaboration shines. Spacecraft with different vantage points and Earth-based photometry under consistent filters can separate real changes from lighting tricks. If everyone sees the same trend after corrections, the physics is speaking clearly. The harsh truth is that some of the most revealing changes can occur during periods when Earth cannot look directly. Solar avoidance rules do not bend for excitement. This is why patience is part of the method. Data taken during the most heated days will travel through spacecraft, downlink, and processing queues before they become plots and frames we can study. The delay is frustrating, yet the physics does not care about our patience. The visitor will carry the record of its trial in its coma and in its fragments if any were created. We will read that record when the sky permits. There is comfort in this cadence. Sublimation is not random noise. It follows rules that we can model and compare against observation. If the inward leg produces outbursts, we can weigh their energy and place them on a scale with known events. If fragmentation occurs, we can measure separation and drift, then infer the forces at work. If colors and spectra change, we can diagnose which ices took the stage and when. Out of glare and delay, a coherent picture can still emerge. As the trial by sunlight unfolds, another human trial runs in parallel. The journey from raw photons to public understanding moves through many hands and checkpoints. That is not a conspiracy, it is a craft. To see why a breathtaking image sometimes takes weeks to appear, we need to walk the path from detector to release. That path is the next part of our story. If sunlight writes the physics on the sky, then laboratories write the story into a picture. Between the moment a photon touches a detector and the moment an image appears in public, there is a long corridor of quiet work. Walking that corridor explains why breathtaking frames often arrive after the moment of peak curiosity. It also explains why a period that feels empty from the outside can be full of patient effort within. It begins with raw signal. Detectors collect electrons as light falls on each pixel. Those counts are not yet a photograph. They are a mixture of target, sky glow, thermal noise, and small quirks in the instrument. To turn this mixture into something trustworthy, teams apply calibrations that remove everything that is not the sky. A bias frame measures the readout pattern imprinted by the electronics. A dark frame maps the thermal current that would register even in perfect darkness. A flat field captures pixel-to-pixel sensitivity, which can vary because no detector is perfectly uniform. These frames are taken close in time to the observation, so that temperature and configuration match. Subtracting and dividing them out turns a raw exposure into a cleaner record of reality. Next comes alignment. Small tracking errors and atmospheric shimmer can shift the target on the detector between exposures. Software aligns the stars and then registers the stack so that signal adds while noise averages away. Cosmic rays leave bright spikes in individual frames. Rejection algorithms identify those spikes and remove them before the stack is combined. When the target itself moves against the stars, the process becomes more complex. For a comet, teams often create two stacks, one aligned on the stars to measure background, one aligned on the moving target to measure the coma, without smearing. The difference between these stacks helps isolate the comet from the night. All of this is still science grey. The next step is to decide what the public should see. That decision is not cosmetic, it is interpretive. A faint tail can vanish if contrast is chosen for the bright inner coma. A bright core can saturate if stretch is optimized for the dim outskirts. Teams experiment with mapping functions that compress the dynamic range while keeping relationships honest. Color adds another layer. Many space images are composites from filters that capture narrow slices of light. Assigning those slices to red, green, and blue produces a view that is informative rather than literal. The intent is to reveal structure and chemistry, not to paint a postcard that misleads. Captions must then explain what colors mean and which parts of the spectrum they represent. Quality control checks follow every aesthetic choice. Astrometry confirms that stars land where they should. Photometry ensures that the brightness scale did not drift during processing. If the image will be compared across nights, the pipeline must be reproducible so that differences reflect the sky rather than software. Independent team members review intermediate products and try to reproduce the result from the starting files. If a feature appears near the detection limit, teams often ask for a second processing pass, with slightly different parameters, to make sure the result is not an artifact. This repetition slows release, but it protects against the most common pitfalls, which are confirmation bias and over-sharpening. There is also the choice of when to publish. Many observatories place scientific results in archives first, where they are available to researchers who know how to handle them. Press releases are reserved for images that carry a clear story for general audiences. The bar is not only about beauty, it is about context. If a picture will raise more questions than it answers, and if those questions require ongoing analysis to address, teams may hold the frame until a short explanatory note or a companion spectrum can travel with it. The goal is not to conceal. The goal is to avoid fueling confusion with half-formed signals. Legal and logistical factors add more time. Some programs include proprietary periods that grant initial access to the proposing team. This practice rewards the effort of planning and executing complex observations. The proprietary clock is finite. When it expires, the data become public by design. Multi-agency coordination adds steps as well. When two or more facilities contribute to a single narrative, their communications offices must synchronize messages and credits. That coordination prevents conflicting statements and ensures that the story is coherent, but it means that all parties wait for the slowest pipeline to catch up. Even the act of writing a caption can take longer than outsiders expect. Words matter. A caption is a promise about what an image truly shows. If a sunward feature might be a projection effect, the text should say so. If a color implies chemistry, the text should describe which lines were recorded and which were inferred. The temptation to oversell a mystery is real. Responsible teams resist it. They choose measured language that invites curiosity without asserting more than the data support. In doing so, they protect future credibility when later results refine the picture. Seen in this light, slow images do not mean slow science. Work continues while the public feed is quiet. Calibrations run. Stacks converge. Spectra are cross-checked. Models are tuned against drafts of the image so that when the frame appears, it arrives with a scaffold of meaning. A person who has waited may still wish for speed, yet the result will be stronger for the wait. This is how one turns photons into knowledge without breaking trust. We can now compare the current case with earlier visitors, whose public timelines felt different. One arrived without a coma, which made measurement clean and debate fast. Another behaved like a textbook comet, which made communication steady and comfortable. Our present traveler complicates both pattern and schedule. To understand why those earlier cases moved quickly, while this one moves carefully, we look next at the lessons they taught and the limits they did not face. The first confirmed interstellar visitor arrived like a riddle carved from rock. It crossed the inner system without a visible coma, so the usual fog of dust and gas that complicates comet studies was absent. That absence was a gift to measurement. Without a shell of light to smear the signal, telescopes could collect precise brightness variations as the object rotated. Those variations became clues to shape and spin. The community built models and argued in public about whether the body was elongated like a shard or flattened like a wafer. The point is not which sketch won. The point is that data could move quickly from detection to debate because the scene was clean. Clean does not mean simple. The object showed a small deviation from a purely gravitational path. a non-gravitational acceleration that is often linked to outgassing in comets. Yet there was no coma to carry the force. That mismatch fueled discussion on every front. Some teams proposed very low-density ices that could evaporate with little dust. Others considered radiation pressure on a very thin body. And still others explored surface processes that might push gently without raising a visible cloud. What mattered for our purposes was the transparency of the process. Light curves, thermal limits, and dynamical fits were posted rapidly. Preprints and talks spread the competing ideas. The public watched science behave as it should, in the open, with uncertainty admitted at every step. Why did communication work so quickly in that case? Geometry and physics aligned. The object was at a phase where it could be observed from many sites with good contrast. The lack of a coma reduced the need for specialized processing. Thermal modeling benefited from a simple surface with no veil of gas to confuse infrared readings. In other words, the problem space was sharp. Teams could make assumptions that were revisable yet reasonable. They could share provisional results that did not require delicate caveats about emission lines or dust scattering. The story moved at the speed of careful curiosity rather than at the speed of caution. That experience also taught a cultural lesson. When an anomaly appears, it is better to bring the conversation into the sunlight than to let speculation fill the gaps. The first visitor generated bold ideas. Some were far-reaching. What kept the conversation healthy was the constant tether to observation. Claims rose and fell on the strength of measurable predictions. If a thin body dominated by radiation pressure was in play, it should behave in a specific way as the phase angle changed. If exotic ices were responsible for the tiny push, there should be consequences for thermal emission. These tests anchored a volatile narrative. The contrast with our current traveler explains much of the difference in cadence. A thick coma introduces ambiguity. Light interacts with grains of many sizes that scatter differently. Gas contributes its own emission. The nucleus hides inside a luminous envelope that blurs sharp edges. Spectra become necessary, yet spectra demand patience and careful calibration. The geometry has also been less forgiving, with the line to the sun narrowing at the very time public interest peaks. The result is a pace that feels slower, not because scientists are less willing to share, but because the data are harder to make unambiguous. There is another quiet lesson from the first case. Negative results matter. A non-detection in the infrared set limits on size and reflectivity. That in turn constrained models of composition and shape. The public often values spectacular images. Scientists also value absences that rule out entire classes of explanation. In a coma-free object, such limits are easier to derive and easier to explain. In a coma-rich case, limits must account for the glowing atmosphere, which absorbs and emits on its own. This complexity delays crisp conclusions. The first interstellar visitor also taught humility about analogies. We looked for familiar boxes to place it in, asteroid or comet, shard or disk. The better approach was to let the data define a new corner of the atlas. A similar humility will serve us now. If a carbon dioxide forward coma and a sunward-looking feature make the current traveler seem unruly, the right response is not to force it into an old category. The right response is to expand the category with clear criteria that can be checked in future cases. Finally, the first event showed that audiences can handle uncertainty when the process is visible. People watched experts disagree without losing trust because the disagreements were disciplined by shared facts. They watched hypotheses evolve as new measurements landed. That is a model worth copying. If the present object requires more time, then the story should be told in installments that respect that need, with each installment labeling what is solid and what is still a sketch. Silence is not required for caution. Clarity is. From an enigma without a veil, we now turn to a traveler that behaved like the textbooks promised. The second interstellar visitor wore a classic coma and tail, and it invited a steady cadence of public images and analyses. That case shows how conformity makes communication easier, and how a familiar playbook can keep curiosity satisfied without drama. It is the natural next comparison before we return to the complexities of our current scene. The second confirmed interstellar visitor arrived with the manners of a textbook comet, a compact nucleus, a developing coma, and a tail that pointed away from the Sunday. In place of paradox, there was pattern. As sunlight rose, the coma swelled, jets appeared as soft fans, and the tail lengthened along the expected direction. Observers could apply the same tools they use on local comets. Photometry mapped a steady brightening trend that matched simple thermal expectations. Spectra revealed familiar volatiles, water, alongside carbon-bearing species that are common in our own outer system. Nothing in the early data demanded a new playbook. The result was a calm sequence of measurements that flowed into public view with little delay. That comfort derived from three advantages. The geometry cooperated, which meant the object could be followed over many weeks at useful solar elongations. The coma was active but not overwhelming, so images retained contrast and inner structure. The chemistry matched expectations for ordinary cometary ices, which made spectral interpretation straightforward. Each of these factors shortened the distance from telescope to explanation. Pipelines did not need custom treatments. Captions could be precise without heavy caveats. Teams could release images and accompanying spectra together, and the story stayed understandable from frame to frame. Regularity built confidence. When a comet behaves as models predict, independent groups around the world tend to converge on the same numbers. Production rates inferred from emission lines agreed within reasonable margins. Light curves corrected for distance followed similar slopes across instruments and filters. The tail morphology responded to phase angle and radiation pressure in the expected way. Even signs of stress later in the encounter, including hints of fragmentation and variability in the inner coma, fit familiar narratives about thermal fatigue and mechanical failure under rising heat. There was novelty in the sense that this was only the second time we had seen a traveler from another system. There was comfort in the fact that its physics felt like home. Communication mirrored that comfort. Observatories shared periodic portraits that documented changes without needing elaborate interpretation. Spectra arrived in step with images and carried clear chemical identifications. Press materials could be written with confidence because the uncertainties were ordinary ones that experts know how to signal. Public engagement followed a smooth arc. Curiosity rose with the object, peaked near maximum activity, then trailed off as it receded and faded. The cadence trained audiences to expect that an interstellar comet could be studied like a local one, and that transparency was the norm when data and models marched together. There is a deeper lesson in that ease. It shows how much of scientific communication depends on the distance between measurement and meaning. When the mapping from raw counts to physical quantities is short and well-trodden, news can be timely without sacrificing care. When the mapping is long, either because the chemistry is unusual or because geometry makes reduction difficult, the pause between observation and explanation widens. The second visitor lived on the short side of that distance. A clean coma, cooperative angles, and familiar lines in the spectrum let teams speak quickly and plainly. Even in that comfortable case, the science was not trivial. Measuring gas production rates requires careful calibration and modeling of how molecules fluoresce under solar radiation. Estimating nucleus size and activity involves separating dust reflection from gas emission and correcting for viewing angle. Interpreting signs of fragmentation demands sequences that can discriminate a transient flare from a structural change. The point is not that comfort means simplicity. The point is that comfort means the tools fit the job without heroic adjustments. Teams could devote energy to extracting precision rather than to fighting ambiguity. This contrast prepares us to appreciate the present situation without suspicion. A traveler that behaves like the second visitor invites quick sharing and frequent updates. A traveler that it departs from those patterns invites slower work and more cautious language. The difference in cadence is not a verdict on intent. It is a consequence of physics and geometry. The second visitor set the bar for what an open and steady investigation looks like when nature cooperates. The current object asks us to accept that nature does not always cooperate, and that patience does not equal avoidance. There is also a strategic takeaway for audiences. When a case follows the comfortable script, it is a chance to learn the baseline, how tails respond to radiation pressure, how spectra evolve as different ices take their turns, how light curves look when activity is smooth. That baseline becomes the ruler we hold against the next object. Without it, every deviation feels dramatic. With it, A deviation becomes a measurement that can be placed within a framework. The second visitor gave us that ruler in a way the first could not, and in a way the current traveler is challenging. We now pause to make the through line explicit, because stories with many threads can blur. Our aim is to pair verified constraints with open questions, to separate method from rumor, and to carry wonder without discarding caution. With that compass reset, we will outline the knowns and unknowns once more, then invite clearly labeled possibilities and the tests that can lift them from speculation to knowledge. Here is the one-sentence compass for our journey so far. We are balancing verified constraints against live questions, and we are letting geometry, chemistry, and measurement decide which is which. This reorientation keeps the through line sharp as the plot thickens. Begin with what has held up. Geometry has been the quiet architect of the public timeline. Solar elongation shrank, so the safest instruments reduced imaging, and most teams pivoted towards spectra or waited for more favorable angles. That constraint is not speculative. It is baked into how observatories survive and how optics behave near glare. Chemistry has supplied a second pillar. Early indications point to strong carbon dioxide activity relative to water, at times when water-driven coma in familiar comets remain modest. That premise does not rest on color alone. It is tied to line detections and to the expectation that more volatile ices can wake in colder sunlight. Measurement forms the third pillar. Photometry is valuable, yet it is fragile unless bands, apertures, and distance corrections are standardized. Where observers align methods, the trends converge. Where they diverge, the scatter grows and rumors follow. Now, set these pillars next to the open questions. How large and persistent is the carbon dioxide envelope once analyzed data emerge? Do spectra from different facilities agree on relative abundances across time? Does the apparent sunward structure trace to projection through dust near the orbital plane? Or does it demand a different mechanism once multi-angle series are compared? Are brightness excursions sustained and coherent across calibrated series, or are they artifacts of mixed practice? Each of these questions is answerable. The path to answers is slower than a headline, but it is clear. Some viewers feel the silence as a narrative of omission. The counterpoint is that absence of a press image is not absence of observation. Pipelines are full during poor geometry. Teams build stacks and test calibrations while waiting for safe angles that allow portraits to join the record. This difference between visible and invisible work creates emotional friction. The right response is to make the method visible without violating the careful pace that real analysis requires. That is why we have spent time walking through elongation, spectroscopy, and photometry with plain language. The more method you see, the less temptation there is to fill gaps with certainty that the evidence does not support. Revisit the anomalies with that method in mind. The carbon dioxide heavy breath is unusual compared with many local comets, yet it is not unphysical. It can arise from layering, from fractures, or from a formative environment where carbon-rich ices were trapped near shallow depths. A sunward-leaning feature can arise when coarse dust accumulates near the orbital plane, and our line of sight runs along that plane. The geometry can create a ridge that crosses the solar direction in projection, even as radiation pressure pushes grains away in space. Brightness jumps can be real when outbursts vent fresh material, or they can be apparent when measurements mix bands and apertures in ways that change the blend of gas emission and dust reflection. These are not exotic conclusions. They are working hypotheses that encourage specific tests. The tests themselves are straightforward to describe. Spectra across multiple epochs with consistent calibration will show whether carbon dioxide remains prominent and how daughter fragments evolve. Multi-vantage imaging sequences will track the angle and contrast of any forward-leaning ridge as geometry changes. Distance-corrected light curves in matched bands and matched physical apertures will reveal whether a sustained excess over thermal expectations exists. When these threads are woven together, the case will clarify. If the object remains unruly, it will be unruly within a narrowed set of possibilities, rather than in a fog of impression. There is also the human dimension to keep. Curiosity abhors a vacuum. The internet rewards confident claims and striking frames. Slow analysis feels like a void that demands filling. This is where a disciplined audience becomes part of the scientific ecosystem. Waiting is not passive when you know what you are waiting for. A checklist converts patience into participation. You are not staring at a blank feed. You are holding a ruler against the next release and asking whether the expected signatures appear. One possibility is that the next wave of data will recast the visitor as unusual but natural. Strong carbon dioxide early, projection sculpted structure, and light curves that settle into distance corrected regularity. A competing view suggests that even after careful reduction, some features will resist easy placement, perhaps due to complex rotation, layered vents, or evolving grain populations that change scattering behavior. It remains uncertain which path the object will follow. What is not uncertain is the set of mechanisms ready to be invoked, and the willingness of the community to label speculation and to separate it from measurement. We have reached a hinge in the narrative. With the foundations and questions arranged side by side, we can afford to look at possibilities that people whisper about when images stall. Speculation has its place when it is framed, tested, and escorted by humility. In the next part, we will state such possibilities plainly, tag them with caution, and describe the observations that could lift them from conjecture to knowledge, or retire them with grace. When data arrives slowly, imagination arrives quickly. That is not a flaw, it is a feature of curious minds. The key is to give imagination a harness. We can state possibilities clearly, mark them as provisional, and tie each to a test that would lift it toward knowledge or set it aside. The goal is not to police wonder, it is to discipline it. One possibility is that the carbon dioxide strength implies an origin in a colder nursery, where CO2 was trapped near the surface, or that layering exposed CO2-rich seams early in the inward journey. This is the conservative picture. It predicts spectra that keep showing robust CO2 bands at large solar distances, then a relative rise in water features as heating deepens. The test is straightforward. Publish a series of spectra with consistent calibration that display the changing balance. If the balance does not change as expected, we ask why, but the method holds. A competing view suggests that the reported green color indicates unusual photochemistry beyond simple dicarbon and cyanogen excitation. It remains uncertain whether processing choices in images amplified that hue or whether fragment production is genuinely elevated. The test again is spectral. A sequence that tracks line strength in the relevant bands against distance and phase angle would distinguish color grading from chemistry. Polarization measurements can add a second check by constraining grain sizes that favor forward scattering, which often enhances the impression of color near the sunward direction. One possibility is that the sunward-leaning feature requires forces outside the standard playbook. A minority view holds that electromagnetic interactions with charged dust could steer material in ways that partially counter radiation pressure. Evidence is limited, but one inference is that charged grains in a patchy magnetic environment could create arcs or kinks that persist as structures. The test is geometry. If the feature maintains a fixed relation to the sun despite large changes in viewing angle and phase, the projection story weakens. If it rotates or fades as the orbital plane tilts relative to the observer, geometry regains the lead. Independent filters that isolate gas lines versus dust reflection would also show whether the feature is particle-driven or emission-driven. One possibility is that light curve jumps record real outbursts linked to rotation that brings vents into sunlight with a rhythm. The prediction is periodicity. A folded light curve that collapses measurements onto a candidate rotation period should reveal repeated pulses. If the pulses migrate in phase or vanish under distance corrections, the rotation story weakens. If they persist and align across multiple observers who use common apertures and bands, it strengthens. Spectral snapshots taken near predicted peaks can check for transient enhancements in fragment lines that often accompany outgassing. A competing view suggests subtle fragmentation that is below the threshold of easy resolution. It remains uncertain whether small pieces can hide within a thick coma and still raise brightness measurably through added surface area. The test is to look for secondary condensations in finely processed stacks that follow the comet rate rather than the star rate. Even a few pixels of excess in a consistent position angle across frames can hint at fragments. Changes in the slope of the coma, brightness profile can also betray fresh surfaces. A multi-night sequence is crucial to separate noise from structure. One possibility is simply that we are seeing a selection effect created by timing. When elongation shrinks, the most photogenic phase overlaps the most difficult viewing phase, so the feed appears to go quiet, and our sense of anomaly rises. The test for this possibility is patience. As elongation grows again, the record should fill with processed images and spectra that cover the interval that felt empty. If those releases show ordinary evolution with a credible CO2 to water transition and projection consistent structure, then the drama lives in the calendar rather than in the physics. There are bolder ideas that people float when the sky goes quiet. A minority view holds that artificial causes could mimic some observed features. Responsible storytelling requires a firm frame here. Evidence is limited, and extraordinary proposals demand overwhelming proof that survives independent reproduction. The only honest test would be repeatable non-gravitational effects, with a clear mechanism that cannot be reconciled with jets or radiation pressure, or material signatures that defy known chemistry in a way that calibration cannot explain. Absent such tests, the idea remains a boundary marker for curiosity, not a working hypothesis. It is useful to remember that multiple weak anomalies can masquerade as a single strong one. A bit of geometry, a bit of unusual chemistry, and a bit of method spread across many observers can add up to a pattern that looks singular. The cure is not to choose the most exciting story. It is to decompose the pattern and test each piece with the right instrument. Spectra decide chemistry. Photometry with standards decides light curves. Multi-vantage imaging decides shape. When the tools align, speculation either graduates or retires. We close this survey by promising to return from possibility to process. Observatories do not run on gossip. They run on schedules, safety margins, and agreements that protect hardware and data quality. In the next part, we will step into that engine room. The engineering clock that governs curiosity explains why some requests are deferred, why some windows are sacred, and why the long arc of discovery chooses durability over speed. Every image we love, and every spectrum we debate, is gated by an invisible clock. It is the engineering clock that keeps observatories healthy, keeps spacecraft alive, and keeps promises to hundreds of research teams who planned years in advance. This clock is not romantic. It is a ledger of constraints. When a rare traveler appears and public appetite surges, the clock does not speed up. It enforces order, so the instruments that serve us today can still serve us tomorrow. Begin with safety margins. Sensitive detectors live behind shields, baffles, and software limits that forbid risky pointings. Star trackers need clean skies to hold attitude. Reaction wheels need momentum dumps that are scheduled to avoid vibration during exposures. Cryogenic instruments need stable temperatures that drift if the sun sneaks into forbidden angles. Operations teams script sequences that keep all of these variables inside guardrails. A request that pushes against a guardrail is evaluated, but the default is caution. Saving a camera from a single risky attempt is worth more than a glamorous frame. These decisions are not secretive. They are the quiet discipline that allows decades of discovery. Next, come queues. Observatory time is promised through competitive proposals. Each accepted program has a list of visits, an exposure budget, and a set of constraints that define when observations make sense. Dynamic schedulers try to honor as many promises as possible while juggling weather for ground sites and thermal or sun angle rules for space missions. Targets of opportunity can interrupt the queue, but they require justification that surpasses simple curiosity. They ask the system to reroute calibration plans, to move staff on short notice, and to accept that some planned data will be lost. When solar geometry is poor and the likely yield is low, the engineering clock prefers to wait for a window that gives science and safety the best chance. Calibration is its own calendar. Instruments drift. Pixels age. Filters gather dust. Teams reserve time for flats, biases, darks, wavelength lamps, and standard star fields. Skip those, and the next night of science becomes harder to trust. People outside the loop rarely see these nights because they produce no dramatic pictures, yet they are the foundation for every measurement that follows. When a new object demands attention, it competes with calibration for slots. The responsible choice is often to defend calibration because an entire season of results depends on it. Downlink and bandwidth matter as well. A spacecraft can gather more data than it can send each day. Antenna time on relay networks is scheduled like any other resource. High-priority campaigns are planned and announced within mission teams because they affect everyone on the link. A surprise long integration on a faint comet can displace routine monitoring of a planet or a long baseline program that cannot be paused. The engineering clock weighs the marginal gain of an improvised exposure against the cumulative cost to other programs. The result rarely favors improvisation unless the case is overwhelming. Multi-agency coordination adds layers to the timing problem. When two observatories plan a joint look, their clocks must align. Thermal constraints on one platform, seasonal weather for a ground telescope, and staff availability for specialized modes all interact. Even if both can observe, their public release calendars must also align so that credits are correct and explanations are consistent. Coordination prevents confusion, but it lengthens the path from photons to press materials. The effect feels like delay from the outside. From the inside, it feels like respect for partners. Data rights are another dial on the clock. Some missions allow brief proprietary periods so that teams who designed and executed a program can analyze first. This practice is not about secrecy. It is about fairness to effort. The periods are finite and codified. When they end, archives open, and the broader community can sift the same photons. If a high-interest target passed through a program with such rights, the public may wait for the curtain to lift. That wait is part of the agreed rules that keep proposal culture healthy. Human limits set the final cadence. Instrument scientists, pipeline developers, and communications staff are not interchangeable cogs. They carry expertise that cannot be conjured on demand. When geometry turns difficult, the same experts are often solving guidance issues, tweaking background models, and advising other teams on safe modes. Asking for instant analysis and instant releases ignores the fact that people must sleep and that careful work takes focused attention. The engineering clock protects people as well as hardware. Seen whole, the system is conservative for good reason. It trades some immediacy for longevity. It protects calibration so that one night of excitement does not poison a year of measurements. It respects agreed cues so that a single story does not silence many others. It slows public releases so that context can travel with pictures. This does not mean wonder is unwelcome. It means wonder is stewarded. Understanding this clock reframes silence. A quiet week can be a week of protection and preparation. A gap in images can be a window where teams gather spectra that survive, glare, or run tests that will make the next safe imaging window count. For the audience, this knowledge is a stress relief. The system is not withholding without cause. It is pacing itself to deliver reliable truth. Every system with rules creates a second-order effect in human minds. When feeds slow, patterns are invented to fill the empty space. That is the psychology of gaps. In the next part, we will turn from hardware to headspace and ask how attention and bias shape what people believe when telescopes go quiet and how to inoculate curiosity against the pull of easy narratives. A silent feed is not an empty room. It is a projector for the mind. When images pause and language turns technical, the brain begins to connect dots that may not belong together. Psychologists have a simple word for this habit: pattern seeking. It is the engine that helps us recognize faces and constellations. It is also the force that can turn coincidence into narrative and delay into design. Understanding this tendency does not scold curiosity, it protects it. Start with attention. Online platforms reward confidence and novelty. A careful update that says more analysis is underway competes with a bold thread that claims a hidden revelation. The bold thread travels farther because it gives the brain a sugar rush. It promises closure rather than process. In times of low signal, this promise becomes magnetic. A person scrolling through short clips will stop when a clear answer appears, even if that answer rests on a single frame or a single anecdote. The reward is immediate. The cost is a gradual divorce from method. Now, add ambiguity. A comet with unusual chemistry and confusing geometry produces messy pictures and plots with error bars. Messy evidence invites stories that are clean. Some will say the quiet means concealment. Others will say the object is ordinary, and that talk of anomaly is marketing. Both are tidy, and both can be wrong in parts. The truth usually lives between them. It contains a pile of caveats and a timeline that feels slow for storytelling. When an audience knows this in advance, the tension eases. When it does not, tribal narratives form, and each tribe selects evidence that flatters its position. Cognitive biases sharpen this drift. Confirmation bias nudges us to notice data that support our starting belief and to discount data that complicate it. Availability bias makes vivid stories feel more common than they are. A viral claim about a dramatic surge in brightness will imprint more deeply than a paragraph that explains filter choices and distance corrections. Anchoring bias sets an early number in our minds. If the first widely shared estimate says a feature is unprecedented in scale, later refinements that cut that estimate by half will feel like retreats, even when they are simply better measurements. These biases are not moral failings, they are shortcuts. We counter them by adjusting the environment rather than by lecturing the audience. One way to adjust the environment is to supply checklists. A checklist is a map that says what to look for and how to weigh it. It turns passive waiting into active observation. When a new frame arrives, a viewer who knows to ask about filter, aperture, phase angle, and distance corrections will spend less time on the color of the glow and more time on the metadata that gives the glow meaning. Checklists also discourage cherry-picking. If every claim passes through the same set of questions, weak evidence becomes visible right away. The habit of asking the same questions each time is a simple antidote to drifting standards. Another way is to narrate uncertainty with care. Uncertainty has degrees. Some are statistical, such as noisy measurements that will improve with more exposure. Some are systematic, such as calibration errors that require new flats or better background models. Some are conceptual, such as incomplete physics that needs a new term in a model. When communicators label the type, audiences can understand what progress would look like. A statistical uncertainty invites more data. A systematic uncertainty invites better methods. A conceptual uncertainty invites competing models that make different predictions. This classification turns uncertainty from a fog into a menu. Trust benefits from visible disagreement inside the rules. People do not lose faith because experts disagree. They lose faith when disagreement seems unmoored. When two teams reach different conclusions and explain exactly which assumptions differ, the public can watch resolution happen in real time. Over a week or a month, one assumption survives and the other yields. The outcome feels earned, and the next disagreement arrives with less rancor. This is how early interstellar debates kept trust intact. The same can happen here if we keep method on the table. Attention also needs rest stops. Every few parts of a long story, it helps to restate the spine. The visitor is interesting because of chemistry that leans toward carbon dioxide, because of a feature that looks sunward under certain viewpoints, and because light measurements have scattered under mixed practice. The next major tests involve spectra across epochs, multi-vantage imaging, and standardized light curves. Any new claim should touch one of these tests. If it does not, it belongs in a parking lot labeled speculation. This habit does not kill wonder. It keeps wonder honest. There is a final lesson in community design. Spaces that reward questions more than declarations retain nuance. If a comment that asks for the filter used receives more likes than a comment that declares a verdict, the tone of the discussion shifts. Moderators and creators can encourage this by praising method in public, and by pinning posts that include raw data and instructions for replication. The message is simple. Participation is welcome, postcards are lovely, procedures are better. We will carry these tools into the next stretch of the journey. The gap between observation and release will open again because geometry and pipelines demand it. When it does, curiosity can either spin or stride. Our aim is to stride. The next part puts that stride into practice by giving a citizen scientist checklist for the coming frames and spectra, so that anyone can read the sky with the same discipline that professionals use. Begin with intent. The goal is to turn waiting into watching. A checklist is not a set of boxes to tick once. It is a rhythm for each new release. You do not need a large telescope to use it. You need curiosity, a habit of reading captions and instrument notes, and a willingness to compare like with like. If you adopt these habits, every image and spectrum becomes more than a postcard. It becomes a piece of a puzzle that you can help assemble. First, read the geometry. Note the solar elongation for the observation and the phase angle between the Sun, the comet, and the observer. These two numbers decide much of what you will see. Small elongation means glare and stricter pointing rules, which explains why a lack of images may not imply a lack of data. Large phase angles often enhance forward scattering by dust, which can make the inner coma look brighter than thermal models alone would suggest. If a frame looks unusually dramatic, ask whether phase geometry gave it a boost. If two frames disagree, ask whether their angles matched. Next, anchor the photometry. Look for the filter used, the aperture radius on the sky, the size of the sky annulus, and the method for zero-point calibration. If these are missing, treat comparisons with caution. If the report includes reduced magnitudes that remove distance to the Sun and to Earth, you are looking at activity rather than simple geometry. If two observers use the same band and a similar physical aperture at the comet, and both see the same trend, the signal is likely real. If one uses clear and the other uses a standard band, or one uses a tiny aperture and the other uses a very large one, differences may reflect method rather than physics. Then, listen to the spectrum. Ask which wavelength range was covered, how telluric absorption was handled for ground-based work, and whether lines for water, carbon dioxide, cyanogen, or dicarbon were reported. A single spectrum can be suggestive. A sequence across days is stronger. If carbon dioxide remains strong while water grows with decreasing solar distance, that pattern fits the idea of a carbon-forward coma that later admits a water phase. If color images look greener, spectra should confirm fragment lines, rather than leave the hue to processing choice. Shape deserves its own pass. When you see a sunward-leaning feature, check the time and the orbital geometry. A feature that changes angle or fades as the viewing plane shifts supports the projection explanation. A feature that locks to the solar direction regardless of geometry demands a harder look. In both cases, ask whether filters isolate dust reflection or gas emission. Dust-dominated features will follow scattering rules. Gas-dominated features will track emission and may look different through narrow bands. Search for rhythm in the light curve. If someone claims periodic brightening, fold the measurements on the proposed rotation period and see whether peaks align across nights. True rotation-driven pulses will keep time within reasonable scatter, even as distance slowly changes. Outbursts will look like sharp rises, followed by slower fades. They may correlate with spectral changes that show fresh fragments. A clean rotation signature can coexist with the slow rise that distance produces. Separate the two by correcting for geometry first, then, looking for leftover periodicity. Watch the coma profile. If a new outburst occurred, the brightness should fall off more steeply near the nucleus, shortly after the event, then relax as the coma expands. If fragmentation began, the profile can flatten, and secondary condensations may emerge as subtle knots that move with the comet across frames aligned on the comet rate. These knots will persist over multiple exposures, while cosmic rays will not. If teams publish stacks aligned on both stars and comet, study both. Subtracting the star-aligned image from the comet-aligned image can reveal faint structures that the eye alone might miss. Respect limits and look for replication. A single report of an unusual line or a surprising spike can be a seed. It becomes a finding only when a second group, preferably with a different instrument, records the same thing with compatible methods. When you post or share an image, include your filter, aperture, exposure time, and calibration notes. When you read a post, praise those who share such details. Communities grow rigorous when rigor is rewarded. Finally, write a short field note for each new data point. One paragraph will do. Record the geometry, method, any clear changes in spectrum or morphology, and whether the light curve fits distance-corrected expectations. Close with a single question you want the next observation to answer. This habit keeps attention from drifting and creates a personal archive that will make sense when the processed flood arrives after the geometry improves. With a checklist in hand, you are ready for the fork ahead. The next observations will likely sort the story into a small number of paths. Ordinary heating and dust physics may dominate. Unusual but natural behavior may persist. Or enduring anomalies may demand more data before judgment. In the next part, we will describe those paths and the markers that separate them. so that when fresh frames appear, you can call the play without waiting for the headline. At this juncture, the story branches into 3 clear paths. Each path has markers that you can watch for with the checklist already in hand. None requires faith. All depend on signatures that instruments can reasonably capture. The outcome will not choose a side in a culture war. It will fall where the data pull it. Path 1 is the ordinary comet path. In this path, the visitor continues to behave according to familiar thermal physics. Carbon dioxide leads at larger solar distances, then water gains strength as heating deepens. Spectra across weeks confirm a transition in relative line strengths. The sunward-leaning feature softens or rotates out of alignment as geometry changes, which fits a projection through dust near the orbital plane. Light curves corrected for distance and phase align with simple sublimation models within ordinary scatter. Outbursts occur as brief events that relax into the baseline rather than redefining it. Imaging shows a steady fan and a classic antisolar tail that grows as radiation pressure shapes fine dust. Occasional small jets add texture, and the inner coma brightens and fades with rotation, but not beyond what past comets have displayed. This path still offers surprises in detail, yet it does not ask for new physics or unusual origins. The visitor goes into the ledger as unusual in emphasis, not unusual in kind. Path 2 is the unusual yet natural path. In this path, the carbon dioxide-dominated phase is stronger and more persistent than familiar cases. Spectra confirm robust CO2 bands across a distance range, where water would normally dominate, and the shift toward water arrives later or remains incomplete. The sunward-leaning feature persists longer, yet multi-vantage sequences still tie it to projection effects and to coarse grains that favor forward scattering. Light curves remain elevated above simple thermal models, yet the excess is coherent across observers and filters once methods are standardized. The coma carries evidence for complex grain populations, perhaps with an abundance of larger particles that resist radiation pressure and build a bright lane near the orbital plane. Outbursts are more frequent or more energetic than average, possibly tied to a rotation pattern that repeatedly exposes a fractured region. Fragmentation may leave subtle knots that hold together over days. This path stretches the envelope of known behavior, but still fits under the umbrella of comet physics. The narrative then becomes comparative. Where did the visitor form that would trap such CO2 near the surface? What layering or plumbing would sustain that flow? What rotation states favor the observed rhythm? Path 3 is the unresolved anomaly path. In this path, multiple threads resist a clean fit, even after careful reduction. Spectra from different facilities disagree on relative abundances in ways that exceed calibration differences. The sunward-leaning feature remains locked to the solar direction, despite large changes in geometry, or it appears in filters that isolate gas emission in a pattern that is hard to reconcile with projection through dust alone. Distance-corrected light curves from calibrated series do not converge, or they remain elevated by a margin that cannot be explained by forward scattering or outburst sequences. Imaging hints at structures that repeat in ways that do not match dust dynamics models, for example, a fixed angle ridge that persists across phase changes, or a symmetry that survives rotation. It remains uncertain whether such signals would survive deeper scrutiny. Evidence is limited, and history favors the idea that better data will untangle the knot. If a durable anomaly remains, the responsible response is not to leap to exotic conclusions. It is to design new observations that target the stubborn pieces with instruments and geometries tailored to them. How will we distinguish among these paths in practice? Spectra will decide the chemistry, a sequence that tracks CO2, water, and common fragments across time with consistent calibration will either confirm a normal handoff, confirm a prolonged carbon-forward regime, or remain contradictory. Multi-vantage imaging will decide the geometry puzzle. If a forward-leaning spine changes as the orbital plane rolls under our line of sight, projection wins. If it does not, a more complex mechanism is implicated, perhaps involving charged grains or gas dynamics that have been underestimated. Photometry with agreed filters and apertures will decide the brightness question. If excess above models persists across independent groups, it is real and must be explained by physics rather than by method. There is a unifying caution that applies to all paths. Patterns drawn from single nights are fragile. The coma is a moving atmosphere, and rotation adds a clock that smears any snapshot. Whenever possible, prefer sequences to moments. Prefer joint analyses over solitary claims. Prefer measurements that arrive with uncertainties and methods to posts that trade method for certainty. These preferences do not slow understanding. They prevent detours that waste months. Each path has a constructive next step. Ordinary behavior invites comparative studies with local comets to quantify how carbon dioxide can lead without rewriting the rules. Unusual yet natural behavior invites deeper modeling of layered interiors, rotation states, and grain populations, along with targeted polarimetry and thermal measurements. Unresolved anomalies invite new campaigns that exploit different vantage points, such as orbiters, wide-field solar images, or future windows, when elongation is generous and calibration is straightforward. The next observers in line are not only on Earth. Spacecraft around other worlds and probes near the Sun can help decide which branch we are on. In the next part, we will ask what they can add during times when Earth-based viewing is compromised, and how their data will stitch into the record that is already forming. When Earth slides into poor geometry, the sky does not go blind. Other vantage points pick up the thread. Spacecraft circling a nearby planet, or probes spiraling close to the Sun, see the visitor from angles that our telescopes cannot. They carry cameras and spectrometers tuned for their primary missions, yet many can be repurposed to catch a comet in flight. What they lack in close-up detail at long range, they repay with continuity, with distinct phase angles, and with backgrounds free from terrestrial weather and day-night cycles. Begin with orbiters around a neighboring world. Their cameras are designed to study canyons, clouds, and dust storms, which means excellent stability and well-understood calibration. At tens of millions of kilometers, the nucleus is unresolved, but the inner coma and the near tail still leave signatures. A shallow gradient, a skewed brightness peak, a faint secondary knot that remains fixed relative to the core across frames, all become measurable. Because these platforms operate above an atmosphere, they can run sequences that stretch across hours without interruption from twilight or cirrus. This is perfect for testing whether a sunward-leaning ridge rotates or fades as geometry changes, and whether the inner coma pulses with a rhythm tied to rotation. Spectrometers on planetary orbiters can also help. Instruments that sniff a thin atmosphere are sensitive to faint emission lines. Pointed toward deep space, they can record the same bands that ground-based observers chase. Carbon dioxide leaves broad features. Fragments such as dicarbon and cyanogen carve narrow peaks. Even low-resolution spectra can detect these if integration times are generous, and if stray light is controlled. The value is not resolution for its own sake. The value is a time series taken from a different seat in the theatre, often at a phase angle that boosts forward scattering or suppresses it, which changes how dust competes with gas in the measured light. Phase geometry is the secret gift of off-Earth observers. From Mars, a comet may be seen at a phase that Earth cannot reach during the same week. Forward scattering by certain grain sizes enhances brightness along the line toward the Sunday backscattering suppresses it. Measuring the same structure at two phase angles close in time constrains grain populations and helps to decide whether a bright ridge is dust, gas, or a blend. It also cross-checks light curve claims. If a rise seen from Earth vanishes at a phase that should emphasize it, lighting, rather than activity, may be responsible. Now turn to probes near the Sunday. Wide-field heliospheric imagers watch the solar wind and coronal structures as they sweep outward. Their fields sometimes capture comets as diffuse streaks against the glow of space dust. They live with glare as a daily condition, so their optics and processing pipelines are built to survive it. When a comet approaches the inner regions, these instruments can follow the development of the tail and the overall coma, even during periods when Earth-based telescopes are constrained by safety limits. The cadence can be high, with images every few minutes or hours, which turns the evolution of outbursts into a movie rather than a before and after pair. Close solar probes also carry instruments that measure the plasma environment directly. While they will not resolve a comet at great distance, they can record changes in the solar wind that a large coma might imprint, such as subtle shifts in density or magnetic structure along a line of sight. If an interstellar visitor carries a vast envelope rich in carbon dioxide that later breaks into fragments, The resulting dust and gas could interact with solar wind streams in ways that leave signatures. Correlating such changes with imaging sequences could test whether unusual morphology has a plasma component or whether dust dynamics alone suffice. Pointing and safety. Rules still apply. Planetary cameras are guided by star trackers that are tuned for the planet below. Tracking a faint moving speck requires special command sequences, and those sequences must be tested to avoid losing lock or saturating sensors. Heliophysics imagers must guard against bright objects near the field that can seed stray light. Operations teams weigh these risks against the potential payout. Even a modest program becomes a victory when it produces a clean time series that bridges an Earth-based gap. Stitching these data into the broader record depends on calibration. The absolute brightness scale of a planetary camera is not the same as that of a large ground telescope. Spectrometer line profiles differ with instrument response. The key is relative stability. If each platform is stable within its own system, cross-calibration can be built using stars in the field or using repeated observations of the same deep sky reference. Once done, joint modeling can combine the threads. The result is not a collage. It is a coherent map that shows how chemistry, morphology, and brightness evolve along a path that no single observer could follow alone. There is also a human advantage. Data that come from independent teams and instruments carry independent biases. When their conclusions converge, confidence grows without needing rhetorical force. When they disagree, the differences illuminate weaknesses in models or methods that would have remained hidden in a single stream. Either way, the science moves. Even with these assets, the public will not always see the product immediately. Downlink schedules, processing pipelines, and careful coordination with partner missions all add time between capture and release. That delay is not a cliffhanger tactic. It is an artifact of responsible practice. In the next part, we will step through how institutions can share unusual results without turning them into sensational claims, and how thoughtful communication keeps trust high, even when the sky refuses easy answers. When evidence is complex and geometry is unkind, the hardest task is not the measurement, it is the telling. Institutions that study the sky carry a double responsibility. They must protect the integrity of the data, and they must protect the public's trust. The first requires meticulous method. The second requires language that is accurate without being arid, and careful without being evasive. Good communication does not rush to fill every silence. It turns silence into a map of what is being done and why. Begin with provisional language. Scientists use words like consistent with, suggests, and indicates, because they are promises about what the evidence can bear. A sentence that admits uncertainty is not hiding the truth. It is marking a boundary. When a team says that a line likely belongs to carbon dioxide, they mean the calibration is strong, yet they are waiting for a second instrument to confirm the identification, and for a model to show that blending with nearby features is not misleading the eye. When a team says a light curve excess may exist, they mean standardized methods are beginning to converge, yet the error bars still overlap with the model that predicts a smooth rise. Such phrasing can feel unsatisfying to a reader who wants a verdict. It is the right phrasing anyway, because confidence that is earned slowly endures. Next comes clarity about process. A concise explanation of pipeline steps disarms suspicion. Tell people that the observation went through bias subtraction, dark correction, flats, alignment on the comet rate, and star-aligned stacking for background checks. Tell them that a colleague repeated the reduction independently and obtained the same result to within a stated tolerance. Tell them that spectra were corrected for atmospheric features using standard stars on the same night, or that a space-based spectrum was cross-checked against a calibration lamp. This level of detail does not bore an audience. It educates the part of the audience that becomes a bridge to the rest. The public does not need every parameter. It needs a sense that the house has a foundation. Context prevents drama from distorting meaning. If a green hue appears, say that such color commonly tracks with fragments like dicarbon and cyanogen, and that confirmation depends on lines in the spectrum rather than on image processing alone. If a sunward-leaning ridge appears, remind readers that projection through dust near the orbital plane can create such features when the viewing angle aligns, and that multi-vantage sequences will test this directly. If brightness claims race across social feeds, show a reduced plot that removes distance and phase, then explain what excess would count as significant. Context does not put out curiosity. It gives curiosity direction. Consistency across channels matters as well. When multiple observatories contribute to a story, differences in phrasing can breed false conflict. One team might say a feature is tentative, another might call it likely. Both may be looking at the same evidence through the lens of different internal standards for the use of words. Coordinated releases prevent this by agreeing on common descriptors and by linking to the same figures and tables. This is not message control for its own sake. It is an alignment of definitions so that the audience can compare apples to apples. Visual honesty is another pillar. Images should include scale bars, orientation, and filter labels. Color maps should be explained in plain language. If a feature sits near the noise floor, show a version with gentle stretch and a version with enhanced stretch. Then say which is better for science and which is better for illustration. If a processing choice suppresses a halo in order to reveal a faint jet, state that choice in the caption. When a reader knows what they are looking at, trust climbs. When a reader discovers a quiet trick later, trust slides. Timing is delicate. There is value in releasing a frame or a plot while the moment is still fresh. There is also value in waiting for a companion spectrum or for a second night that repeats the signal. The rule of thumb is simple. Share early when the evidence is robust at a basic level. For example, a bright tail seen under good geometry, or a line that stands far above noise. Hold longer when interpretation depends on subtle distinctions, for example, a weak excess that could be method, or a structure that projection could mimic. Early, accurate, and modest beats late, flashy, and wrong. Finally, include the next test in every communication. If a team reports strong carbon dioxide emission, tell people that a rise in waterlines is expected as the object warms, and that sequences in the coming weeks will check this. If geometry is suspected in a sunward feature, point to the dates when the viewing angle changes and say that the feature should rotate or fade if projection is responsible. If photometry hints at periodic pulses, share the candidate rotation period and invite independent observers to fold their data and look for phase alignment. This practice converts audiences from spectators into partners. It also inoculates against speculation by stating in advance what would count as confirmation or refutation. Communication that resists the cliffhanger does not drain drama. It replaces cheap suspense with durable intrigue. The plot still has turning points. They arrive when a predicted line appears, when a ridge swings with the plane as forecast, or when a light curve settles into a pattern that a model predicted. Those are better cliff edges, because they are cut by reality. With that in mind, we return to the spine of the science. Chemistry, shape, and light remain the three hinges of this story. In the next part, we restate them in compact form and prepare to dive deeper into the geometry that makes a sunward appearance from ordinary dust. Before we push further, set the frame again. Three threads carry this story: composition that appears to give carbon dioxide an early lead, morphology that includes a feature leaning toward the sun in some views, light behavior that has looked scattered under mixed methods and steadier where practice aligns. Keep those threads together, and the map through the next turns stays clear. Start with chemistry. Comets are time capsules. Their volatiles record the temperature and pressure of formation, then their layering and fractures decide how that inventory vents. When carbon dioxide speaks louder than water earlier than usual, it hints at shallow CO2 reservoirs, or at plumbing that favors those reservoirs under modest heating. Spectra will refine the picture as processed data arrive. A sequence that shows persistent CO2 at distances where water often takes over would not be an impossibility. It would be a clue to where and how this nucleus assembled its layers. If, instead, water lines rise decisively as the sun climbs in the sky, we will have watched a handoff that fits the usual order. Either way, chemistry is the honest narrator because lines tie directly to molecules rather than to opinion. Now shape. The eye loves structure. Bright ridges look like intention. Physics loves projection. Dust grains, lifted by gas that flows along vents, populate a thin sheet near the orbital plane. Viewed nearly edge-on, that sheet can place a lane of brightness along the line toward the sun, without violating the rule that radiation pressure pushes dust away. Synchrone and syndine families describe this dance. The trick is to watch angle and time. If the ridge turns or fades as the plane rolls under our line of sight, geometry wins. If it stays nailed to the sun in every configuration, the model is incomplete and more ingredients must be added. Perhaps charged dust dynamics, or a gas emission component that masquerades as a dust spine in broadband images, filters, polarimetry, and sequences. From different vantage points will give the verdict. Finally, motion. Light curves are motion translated into brightness. Gas production rises with heat, rotation modulates the view of vents, and outbursts add spikes when crusts burst. The danger lives in method. Mix filters and apertures and geometry corrections, and a chart becomes a collage. Clean the practice, and the picture clarifies. Reduced magnitudes that remove distance to the sun and to Earth convert a raw arc into activity. Matching bands and using apertures that correspond to the same physical size at the comet turn separate observers into a single instrument. Once that discipline is in place, 3 signatures matter. A smooth rise that follows sublimation models, brief jumps that relax as comae expand, and periodic wiggles that hint at rotation. When those signatures are read together with spectra and images, motion stops being gossip and becomes constraint. These threads are not separate lanes, they braid. Composition sets, which ices wake first, which sets the gas that carries dust, which sets the grain sizes that dominate scattering, which sets the shape we see, which feeds back into how bright the coma looks through a given filter and aperture. The reason to restate this braid is simple. It inoculates against single-frame conclusions. A green tint without spectra can be a processing choice or a true fragment signature. A ridge near the sun without a geometry check can be a projection. A light curve surge without distance correction can be an illusion built by phase angle and lens choice. Tie each claim to its partner threads, and you will waste less time chasing phantoms. There is a practical way to hold this braid while news trickles in. Use 3 questions each time a new release lands. What did chemistry do? Which lines were measured? And how did their ratios change? What did shape do? Did structures rotate, fade, or sharpen as viewing angles and filters changed? What did motion do? Did reduced light follow a model, jump like an outburst, or pulse with a period? If one question cannot be answered because the data type is missing, note that gap and do not let the other 2 outrun it. A single strong piece can point, but only a pair or a trio can pull. We also hold space for surprise. A nucleus can carry odd rotation states with tumbling that confuses simple periodicity. Vents can self-shadow and produce rhythms that drift. Grain populations can evolve as larger fragments grind down, changing the scattering phase function and the look of the inner coma. None of this requires exotic intent. It requires careful watching. Surprise is precious in this field. It draws better tests and forces sharper models. The task is to honor it without letting it harden into premature myth. With the compass reset, we can give the geometry puzzle the room it deserves. Many viewers have asked how a tail or a ridge can look as if it leans toward the Sunday. The answer is a patient lesson in perspective that does not drain the wonder from the image. It adds it. In the next part, we will walk through the way dust sheets and viewing planes conspire to paint a sunward illusion, and how a simple change in vantage can turn a paradox into a diagram. Begin with a picture in your head. Place the comet on a racetrack that lies nearly flat, a thin plane, where dust shed over days and weeks stays close to the orbital path. Grains leave the nucleus with many sizes and speeds. The smallest feel the push of sunlight most strongly and rush into a delicate anti-solar tail. The larger ones barely notice that push. They slide along with the comet and pile into a narrow sheet that hugs the path. Now put your eye almost edge onto that sheet. A lane of dust runs straight through your line of sight. That lane brightens not because the dust moves toward the sun, but because a long column of material is stacked along your view. The lane can cross the solar direction in projection, which tricks the brain into reading forward when the physics is pushing backward. 2 families of curves help turn this picture into a method. Synchrones group particles by the time they left the nucleus. Syndines group them by how strongly they respond to radiation pressure, which depends on size and composition. Where multiple synchrones and a syndine align in our view, the sky paints a ridge. If our line of sight happens to lie near the orbital plane, the ridge can fall close to the sun on the image. This is an honest illusion. It is three-dimensional structure painted on a two-dimensional sensor. A simple way to test this is to let the stage rotate. As the comet advances, the angle between the orbital plane and our line of sight changes. If the ridge is a projection through a dust sheet, its apparent angle and brightness should evolve with that rotation. Seen more face-on, the sheet looks broader and the ridge softens. Seen more edge-on, the sheet tightens and the ridge sharpens. In some geometries, the ridge appears to cross the nucleus and extend beyond it, which observers call an anti-tail. The same comet can show a perfect anti-solar tail and an anti-tail in the same season, only weeks apart, because the audience has shifted seats in the theater. Light adds a second layer. Dust grains do not scatter light evenly in all directions. Many populations prefer to scatter forward. This means that material along the line to the sun can appear brighter than material at the same distance in another direction, even if the physical density is the same. Instruments record this bias as a phase function, which is a curve that describes how brightness changes with the angle between the sun, the dust, and the observer. If a ridge lies near the solar direction and the grains favor forward scattering, the ridge gains contrast. A careful model multiplies the dust column by the phase function to predict how bright the ridge should appear for each geometry. Color and polarization separate dust from gas. If the ridge is primarily reflected sunlight, its spectrum should look like sunlight modified by the grains. Polarization should be consistent with the size range that favors forward scattering. If the ridge is instead dominated by emission from molecules, narrow-band images through filters that isolate specific lines will make it stand out differently, or not at all, compared with broadband light. Sequences that alternate filters across the same geometry can draw this distinction even when resolution is modest. There is a temptation to explain any sunward-leaning feature with an unfamiliar force. Resist that until the projection test fails. Ask for multi-vantage views taken within the same week. A planetary orbiter can see from one angle, while Earth-based telescopes see from another. If the ridge changes position relative to the sun between the two views, dust sheet projection is the likely cause. If the ridge stakes out the solar direction regardless of angle, and if it persists in narrow-band gas images while fading in dust-dominated bands, then gas dynamics or charged particle forces may share responsibility. That would be an interesting outcome, but it is the second hypothesis rather than the first. Practical tools make this more than a thought exercise. Software can plot the expected synchrone and syndine geometry for a given orbit and date. Overlaying those curves on images shows whether a bright lane aligns with the predicted families. Observers can publish the angle of the ridge relative to the anti-solar direction, along with the date and phase angle. Plotting that angle against time reveals whether the ridge turns as geometry changes. In many well-studied comets, the plot traces a smooth curve that tracks the changing viewpoint. We should expect the same behavior here, unless another ingredient is at work. The large carbon dioxide coma discussed earlier supports the projection route. A strong CO2 flow can lift more large grains into the orbital sheet. More large grains mean a stronger lane. A greenish tint reported in some images does not settle the issue. Spectra must confirm fragment lines before color is treated as chemical proof. Until then, color can be a mix of dust scattering and weak bands that processing choices have emphasized. Even if projection explains the sunward look, the lesson remains beautiful. Nature has composed a three-dimensional sculpture that reveals itself only when the audience sits in just the right place. The sculpture rearranges as the comet moves, and as we move. Our task is to track the dance with geometry and with light, so that a trick of perspective becomes a tool rather than a trap. With geometry clarified, we return to the quiet arithmetic of light. Properly reduced brightness carries an independent test of any geometric explanation. If projection is responsible, the light curve should still obey the rules of heating once distance and phase are removed. If it does not, then activity or outbursts are adding their own story on top of the view. In the next part, we will read that light with patience and show how time series settle debates that single frames cannot. Light is the simplest currency in astronomy. Count photons, correct for geometry, and you have a measure of activity that ignores the drama of a single frame. A comet complicates this only by adding an atmosphere that grows and drifts. The cure for that complication is patience. Time series photometry turns snapshots into a narrative that can confirm projection effects or reveal genuine changes in gas and dust production. When we read light this way, we can separate what the eye wants to believe from what the physics insists upon. Begin by removing the easy trends. Distance to the sun controls energy input. Distance to the observer controls how diluted the reflected and emitted light appears. Reduce the observed magnitudes to a standard distance from the sun and a standard distance from the observer. The remaining curve is the comet's activity written as brightness. A smooth rise that follows common sublimation laws points to ordinary heating. A curve that rises more quickly than models allows signals either a real excess in production or a problem with method. We can test this by asking whether the excess survives when the phase angle is included. Large phase angles enhance forward, scattering by dust, and can mimic surges. Apply a phase function that matches the grain sizes suggested by polarization or color. If the excess persists, the case for a physical change strengthens. Next, separate dust and gas. Broadband filters mix both. Narrowband filters can isolate specific contributors. A series in a gas-sensitive band measured side by side with a series in a dust-sensitive band can show whether an increase is chemical or particulate. If a rise appears only in the dust band, changing grain populations or improved forward scattering may be at work. If it appears only in the gas band, increased sublimation is favored. If both rise, the nucleus has likely warmed into a more active state and is sending both components into space in greater quantities. Rotation draws a finer pattern over the slow trend. Vents come in and out of sunlight, shadows cast by terrain open and close pathways for gas. The result is a weak periodic modulation that rides on top of the overall brightening. To reveal it, fold the reduced light curve on trial periods and look for alignment of peaks across nights. A consistent peak that keeps time is a sign that geometry on the surface is controlling the view. A peak that wanders may reflect changing projection as the viewing angle shifts, or it may reflect genuine evolution in the venting pattern as heat penetrates deeper layers. Either way, a folded curve replaces impression with measurement and sets up predictions that future nights can confirm. Outbursts write a different signature. They rise quickly and fall slowly. The inner coma brightens first, then the steep profile relaxes as the material expands. If you have both photometry and aperture growth curves, you can watch the brightening propagate from small apertures to larger ones over hours. Spectra taken during the rise often show enhanced fragment lines. These signatures guard against mistaking a cloud break or a processing choice for an event. They also allow energy estimates. Count the excess light above the baseline, translate it through standard assumptions about grain sizes and albedo, and you have a rough measure of the mass thrown into space. Method can still betray us if we become careless with apertures. A fixed angular aperture samples a different physical scale as the distance to the comet changes. That can alter the recorded fraction of the coma that your measurement reports, especially during outbursts that move through the inner regions quickly. A better practice is to choose an aperture that corresponds to a fixed physical radius at the comet. Then adjust the angular radius to match each night. This keeps the measurement tied to the same physical zone and makes the series more comparable across the geometry changes that a long encounter brings. Consistency across observers is the final defense against flattering artifacts. Agree on bands when possible. Share aperture sizes and sky annulus choices. Use stars from the same catalogue to set 0 points. When a rise appears in several independent series that share these standards, skepticism can relax. When a rise appears only in series that mix bands or apertures, or that lack distance and phase corrections, patience should win. This does not dismiss the effort of enthusiastic observers. It honors the fact that comae are subtle and that small differences in method can look like physics. Reading the light over time also feeds back into the shape story. If a sunward-leaning ridge is largely projection, the reduced light curve should still follow heating once phase is accounted for. If a leaned ridge coincides with a sustained excess in gas-sensitive bands, then geometry is not the whole answer. The ridge is likely riding a real increase in production that made the sheet brighter, at the same time that viewing angle boosted its contrast. This is why curves and pictures belong in the same folder. Each explains the other when the clock is allowed to run. There is one more virtue to patient light. It creates a shared schedule. If the curve predicts a rotation pulse on a particular night, imagers can plan narrow windows to catch the inner coma at its most textured. If the curve shows a plateau that should break when the comet enters a new thermal regime, spectroscopists can request time near that date to test for a change in line ratios. In this way, photometry becomes a conductor for an orchestra of instruments that cannot all play at once. We will use that conductor in the next movement. As the visitor leans into stronger sunlight, the question turns from what we can measure to how we prepare for the most revealing window. The plan is simple. Identify the moments when geometry improves, match them to the expected chemical and rotational milestones, and line up eyes on Earth and in space. In the next part, we will set that campaign so that when the sky opens, the story does not just resume, it accelerates. The best antidote to ambiguity is preparation. Geometry will improve, elongation will widen, and safe pointing will return. Before that window opens, we can set a plan that turns the first clear nights into a decisive test of chemistry, shape, and light. The plan does not need secret assets. It needs shared calendars, agreed methods, and a simple division of labor between wide nets and sharp spears. If we begin now, the first wave of frames and spectra will arrive already connected to the questions that matter. Start with a shared clock. List the dates when elongation grows enough for major facilities to image, without flirting with safety limits. Add the times when phase angles change quickly, since those days will stress the projection hypothesis about any sunward-leaning ridge. Include the predicted windows for rotation pulses, inferred from preliminary light curves, even if the period has uncertainty bands. Publish this calendar in a format that can be read by amateurs and professionals alike. A simple sheet with universal time, expected geometry, and suggested instruments will synchronize hundreds of small choices into a single campaign. Assign roles by strength. Large space telescopes and big ground observatories with stable spectrographs should anchor the chemistry thread. Their task is to deliver a sequence of line measurements that track carbon dioxide, water, and common fragments across the first weeks of improved visibility. The choice of consistent wavelength coverage and calibration standards will matter more than pushing resolution to the limit. Medium-sized telescopes with wide fields should own morphology, delivering time series imaging that compares broadband light with narrow bands tuned to gas lines. Small telescopes with reliable photometry should supply dense light curves in agreed bands and apertures tied to a fixed physical radius at the comet. Each role is valuable because each fills a gap the others cannot. Pre-register the tests. For chemistry, state in advance that a rise in water lines relative to carbon dioxide is expected as the object warms, and that a persistent carbon dioxide dominance would be a genuine surprise that demands interior models with shallow reservoirs or unusual layering. For shape, state that a ridge should rotate or fade as the orbital plane tilts, and that persistence locked to the solar direction across angles would point to additional physics that images through gas-sensitive filters should probe. For light, state the baseline sublimation model and the phase function to be used, and that a sustained excess above the corrected curve across independent series will count as a real change in output. Writing these tests down converts arguments into experiments. Engineer the handoffs. If a photometric network sees a rotation pulse on a particular night, imagers can schedule sequences to catch the inner coma when jets are most textured. If imagers record a possible fragment, spectroscopists can aim for lines that might strengthen near fresh surfaces. If spectra show a sudden change in fragment ratios, photometrists can watch for corresponding color shifts and outburst signatures. A shared channel for quick look notes will make these handoffs fluid. The notes should be minimal, just enough to move the ball without preempting careful reduction. A sentence that says, a narrow band line rose by a clear factor, or that a ridge changed angle by a stated measure will do. Guard the pipelines. The urge to rush a glamorous image is understandable. Resist it until calibration and checks are complete. Teams can prepare by rehearsing their reductions on archival comets with similar brightness and geometry. That rehearsal will harden scripts and expose weak spots before the new data land. Communications leads can draft captions that already include scale bars, filter labels, and plain descriptions of processing choices, so that the first public frames arrive with context. Amateur leaders can share templates for photometry reports that standardize the way aperture sizes, sky annuli, 0 points, and reduction choices are recorded. Rigor moves faster when it is pre-built. Invite replication on purpose. Pair observers across longitudes and hemispheres so that a claim recorded at dusk in one place can be checked before dawn in another. Encourage combinations of instruments that differ just enough to reveal calibration problems without masking real signals. Ask at least one group to act as a control by repeating exactly the same method night after night with no tuning to chase features. When discord appears, let method decide as quickly as possible, by isolating what differed. The goal is not to win an argument. It is to eliminate error bars that come from practice rather than from space. Plan the archive from day one. Set a common folder for reduced products with clear versioning. Store raw files in official repositories as policies allow. Then mirror key reduced sets in community spaces with metadata. Write brief README notes that explain what each file contains and what steps produced it. This is tedious work in the moment and priceless a month later when comparisons matter most. An organized archive turns a rush of arrivals into a dataset that future students can mine with fresh questions. Finally, promise an early synthesis date. Do not wait for perfection. After the first 2 or 3 weeks of improved visibility, gather a short report that states what chemistry, shape, and light did, and which of the 3 paths the evidence favors so far. Include the next decision points, for example, later rotation checks, later phase angles, or thermal milestones that will trigger new venting. Sharing this synthesis will not close the book. It will show that the plan produced leverage and that uncertainty is shrinking in honest steps. With a calendar posted, roles assigned, tests pre-registered, and archives ready, the window ahead becomes less a hope and more a design. The last piece is to remember why the design exists. Curiosity deserves clarity. Wonder deserves a fair trial by evidence. In the final part, we will step back from schedules and spectra and ask what this episode teaches about how to keep both wonder and rigor alive when the sky sends us something rare. Every rare visitor tests not only our instruments but our habits. The sky offers a puzzle that glows, then hides inside glare, then glows again from a new angle. Audiences lean forward. Scientists retreat into careful steps that look slow from the outside and essential from the inside. Somewhere between those postures is a practice that preserves both wonder and rigor. We end here because the pattern will repeat with the next interstellar traveler. If we learn its rhythm now, the next story will feel less like a tug-of-war and more like a duet. Begin with a promise to curiosity. Mystery is not a defect. It is the engine that brings eyes to the page and hands to the instruments. A carbon dioxide heavy breath challenges expectations shaped by comets that prefer water nearer the Sunday. A ridge that seems to lean toward the sun challenges the intuition we have about tails that should always point away. A light curve that looks jumpy challenges our desire for neat graphs. These tensions do not vanish when the papers arrive. They mature. If we keep the known versus unknown axis front and center, the maturing feels like a reveal rather than a walk back. Next, guard the ruler. The ruler is the checklist and the shared methods. When a frame lands, we ask the same questions each time. What was the geometry? What band and aperture? What calibration? Which lines in the spectrum were measured? And how did their ratios evolve? What did the reduced light curve do once distance and phase were removed? This repetition is not a chore. It is a ritual that turns a flood into findings. It trains an audience to expect metadata as part of the picture, and it trains communicators to include that metadata as a matter of course. Then, respect the craft that stands between photons and meaning. Bias frames and flats are not drama. They are the scaffolds that hold the vault. 2 aligned stacks, one on stars and one on the moving target, are not a flourish. They are the way we separate a faint coma from a crowded field. A caption that names filters and stretches is not a footnote. It is a bridge that keeps trust intact. When institutions let people see these steps, suspicion recedes. Process is not the enemy of awe. It is the way ore survives scrutiny. We also carry forward a better way to label speculation. Possibilities are welcome when they are fenced and tested. A sentence that begins with one possibility invites a future measurement to walk on stage and bow or wave. A sentence that begins with evidence is limited, but one inference tells the mind to hold the thought lightly. A sentence that begins with it remains uncertain whether admits that the next instrument may change the score. This vocabulary does not drain color. It paints with hues that the data can support. Communication wins when it includes the next test. If a strong carbon dioxide phase is reported, tell people that water lines should grow with heat, or that their absence would be a surprise worth modeling. If a ridge appears near the sun, say when the viewing angle will change enough to test projection. If a light curve looks elevated, name the band, the aperture, and the phase function, and invite matches. The public is not allergic to method. The public is allergic to moving goalposts. Tests fixed in advance turn a series of posts into a story with chapters that end on earned turns. Finally, widen the circle of practice. Citizen scientists can run standardized photometry with care. Small telescopes can supply cadence that large facilities cannot. Planetary orbiters and solar imagers can keep watch when Earth must look away. Professional teams can publish reduced products with clear licenses and notes so that students can learn by doing real work. When these communities meet at the level of method, not only at the level of images, the next interstellar story will have more hands to carry it and fewer gaps where rumor thrives. We have carried a single through line from the first quiet moments to the plan for the next clear nights. Geometry set the public tempo. Chemistry gave the visitor its voice. Measurement translated both into claims that can stand. If the object settles into familiar physics, we will celebrate the way unusual details expand the map without tearing it. If the object keeps a few secrets, we will admit them without reaching for drama that data do not deserve. Either way, the lesson is durable. Wonder is sharper when it is measured, and truth travels farther when it invites people to check the steps. The sky will send another stranger. It may breathe a different mix of ices. It may carry dust that tricks the eye in a new way. It may pass during a season when our best cameras must look away again. When that happens, we will be ready with the same compass. Name the constraints, mark the unknowns, tie every claim to chemistry, shape, and light, pre-register the tests, share the archive. Synthesize early, revise often, and keep the door open for better data. Curiosity deserves nothing less. The cosmos rewards nothing more.